Right now, as you read these words, a star is burning 20,000 light-years from where you sit. You will never see it with your naked eye. You will never find it by stepping outside on a clear night and scanning the sky. The dust between you and that star is so thick, so impossibly dense with ancient cosmic debris, that the light leaving its surface has been swallowed almost entirely before it can reach you. In visible wavelengths, this star does not exist for you. It is as though the universe itself chose to hide the most extreme object it has ever produced. But it is there, and what is there will permanently alter the way you understand the word large. The star's name carries the precise, unpoetic quality of scientific nomenclature, Stevenson 2-18, a designation that tells you nothing about what this object actually is, nothing about what it means that it exists at all. Nothing about the fact that if you removed our sun from the center of our solar system and placed Stevenson 2-18 inches its position, the surface of this star would extend outward past the orbit of Saturn. Mercury would be gone. Venus would be gone. The planet you are standing on right now, every ocean and mountain and living creature, every civilization that has ever risen and fallen, every atom of every human being who has ever drawn breath gone, swallowed inside the outer layers of a single star. Mars would be gone. Jupiter, the largest planet in our solar system, the planet that could contain every other world in our solar neighborhood within its volume, would be gone. Saturn, with its magnificent rings spanning distances larger than Earth itself, would orbit just above the churning surface of this stellar monster, dipping in and out of its outer atmosphere with each elliptical pass. That is the scale of what exists in the constellation Scutum 20,000 light-years from Earth. But here is what most people get wrong when they first encounter this number. They hear the largest known star, and they picture something like our sun, only bigger. They scale up the image. They already carry a bright sphere, a familiar disk of light suspended against blackness. They make it larger in their imagination and think they have understood something they have not. Stevenson 2-18 is not simply a larger version of what you already know. It is a fundamentally different category of object operating under physics that our intuition is entirely unequipped to process. Its average density falls below the density of the best vacuum achievable in a terrestrial laboratory. Its surface temperature is cool enough for molecules to form in its outer atmosphere, water vapor, titanium oxide chemistry that would be instantly destroyed on the surface of our own sun. It pulses and breathes over cycles lasting years, its diameter expanding and contracting by distances larger than the orbit of Earth. It loses mass at rates millions of times greater than our sun, shedding the equivalent of our star's entire mass every few thousand years into the surrounding darkness. The question this video will answer is not simply how large Stevenson 2-18 is. That answer, while staggering, is just a number. The question that matters is this: what does it mean that the universe is capable of producing something like this? What physics allows a single star to grow to dimensions that swallow planetary systems? What will happen when this monster dies? And what does its existence tell us about our own place within a cosmos that produces such extremes in silence, invisible to our eyes, hidden behind curtains of ancient dust? If you find yourself drawn to questions that reach beyond the ordinary scale of human experience, that pull you into the deep structure of what the universe actually is, rather than what it merely appears to be, do me a small favor and hit that like button and subscribe. It genuinely helps this channel continue making journeys like this one. Get yourself comfortable. Let's begin. To understand what Stevenson 2-18 actually is, you first need to anchor yourself to something familiar, and then you need to let go of it entirely. Our sun is large, not merely large in some colloquial sense, but large in a way that resists genuine comprehension even when you know the numbers. The sun's diameter measures approximately 865,000 miles. If you wanted to line up copies of Earth side by side across that span, you would need 109 of them. The sun's volume exceeds that of Earth by a factor of 1.3 million. If you hollowed out our star and poured in Earths like water filling a jar, you would need more than 1 million of them before the jar was full. By any standard you can construct from human experience, from the tallest mountain to the deepest ocean trench to the widest continent, the sun is incomprehensible in scale. it is also by cosmic standards entirely ordinary. Our Sun sits comfortably in the middle of the stellar mass distribution. It is neither unusually large nor unusually small. Of the roughly 400 billion stars in the Milky Way, the vast majority are actually smaller and dimmer than our sun-red dwarf stars that glow with a fraction of its energy output and will burn for trillions of years before exhausting their fuel. Our Sun, which will eventually exhaust its hydrogen in another 5 billion years, is already on the larger end of the common range. And yet our Sun's diameter of 865,000 miles must be multiplied by approximately 2150 before you arrive at the diameter of Stevenson 2 to 18, 2,150 times the diameter of our Sun. Try to hold that number for a moment. Not the number itself, which is just a symbol on a page, but what it represents in physical space. You are multiplying a sphere 865,000 miles across by a factor of 2150. The resulting diameter approaches 1.86 billion miles. The fastest thing in the universe, light itself, traveling at 670 million miles per hour, requires more than 2.5 hours to travel from one side of this star to the other. The photons leaving the surface of Stevenson 2 to 18 on one side right now will not reach the opposite surface until long after your next meal, your next night of sleep the next day, has begun. Consider a more tangible comparison because numbers at this scale require anchoring to physical objects you can actually picture. Take a standard basketball. It measures roughly 9.5 inches across. If our Sun were the size of that basketball, then Stevenson 2 to 18 would be a sphere approximately 1,700 feet in diameter. That is taller than the Empire State Building. That is taller than nearly every structure ever built by human civilization. A basketball sitting beside a sphere taller than the most famous skyscraper in the world. That is the size ratio between the star at the center of our solar system and the largest known star in the observable universe, or consider time rather than space. Suppose you wanted to fly around the circumference of Stevenson 2 18 inches, a commercial aircraft traveling at 500 miles per hour, the speed of a typical passenger plane crossing an ocean. The circumference of this star approaches approximately 5.8 billion miles. At 500 miles per hour, your flight would require over 1,300 years to complete. If you had boarded that plane in the year 720 CE, when the Tang dynasty ruled China and the Umayyad Caliphate stretched across the Middle East, you would still be in the air today. You would land sometime around the year 3030. That is the circumference of a single star. But even circumference fails to capture the most extreme aspect of Stevenson 2 to 18's dimensions. Volume scales with the cube of radius. When you increase a sphere's diameter by a factor of 2150, you are not increasing its volume by 2150 times. You are increasing it by 2150 cubed. The mathematics produces a ratio approaching 10 billion to 1. Nearly 10 billion copies of our Sun could fit inside the volume of Stevenson 2 to 18. The number has 10 digits when written in full. Here is what 10 billion means in human terms. If you began counting right now one number per second without stopping, without sleeping, without pausing for any reason, you would reach 10 billion in approximately 317 years. You would need to live from the dawn of the Industrial Revolution until past the year 2300 to finish counting the number of suns that could fit inside this single star. The solar system comparison deserves its own moment of stillness because it is the most personal way to understand this scale. Our solar system is, from a human perspective, vast. The distance from the Sun to Earth measures 93 million miles, a span we call 1 astronomical unit. Light requires 8 minutes and 20 seconds to cross that distance. Traveling at the speed of your commercial aircraft, the journey from Earth to the Sun would take approximately 21 years. The journey to Jupiter, at 5 astronomical units from the Sun, would take over a century. The journey to Saturn, nearly 10 astronomical units out, would take almost 200 years. These distances feel infinite to creatures who evolved on a single planet. Now place Stevenson 2 to 18 at the center of our solar system, its core, where our Sun currently burns. Mercury vanishes. The innermost planet closer to our Sun than any other world exists inside the star's volume. its rocky surface, its craters and plains and cliffs, all of it consumed within the outer atmosphere of this stellar giant before the planet even approaches anything resembling a solid stellar surface. Venus vanishes, the brightest object in our night sky after the moon, the planet whose thick clouds of sulfuric acid reflect sunlight so brilliantly that ancient astronomers named it after the goddess of beauty exists inside the star. Earth vanishes. The only world in the known universe confirmed to harbor life, the pale blue dot that has been the entirety of the human story, the stage on which every war and love story and scientific discovery in our history has occurred, exists inside. The outer layers of Stevenson 2-18. Mars vanishes. The planet toward which we have launched our most ambitious robotic explorers, the world that may one day be home to human settlers, exists inside the star. The asteroid belt vanishes. Jupiter vanishes, taking its 79 known moons with it. Saturn would orbit just above the stellar surface. From a hypothetical moon of Saturn in this configuration, you would not see a sun in the sky. You would see a wall. A vast, dim, crimson wall stretching from horizon to horizon, covering half your entire visual field, radiating a faint reddish heat across a sky that knows no true darkness on the side, facing the star. The concept of day and night as you have always understood it requires a sun that occupies a small portion of the sky. A sun that sets. A sun that creates a shadow. When your sun fills the entire horizon, these concepts dissolve entirely. Uranus and Neptune would survive. They would orbit an object so enormous that from their distances, the star still fills angles of sky incomprehensible by terrestrial standards. This is not a hypothetical constructed to be dramatic. These are the actual orbital distances compared to the actual measured dimensions of an actual star that actually exists in the Milky Way galaxy, 20,000 light-years from the surface you are sitting on right now. The volume comparison with our Sun demands one more pass approached from a different angle because the mind tends to accommodate large numbers without truly absorbing them. Imagine you are filling Stevenson 2-18 with suns, not metaphorically. Physically filling this volume with spheres, each the size of our star, packed together as efficiently as spheres can be packed. You would need approximately 9.8 billion of them before the volume was full. Nearly 10 billion suns. Now consider what 10 billion suns represents in terms of the stellar population of our galaxy. The Milky Way contains an estimated 400 billion stars. If you filled Stevenson 2-18 with suns, you would be using approximately 1 out of every 40 stars in the entire galaxy. You would be emptying 2.5% of all the stars in the Milky Way to fill a single object. This single star on its own contains a volume equivalent to nearly 1/40th of all the stellar volume in the galaxy. And you have never heard its name until recently. It was completely invisible to human observation until infrared telescopes revealed it hiding behind its curtain of dust. This is the star whose story we are following. The question of how anything this large can exist, what physics permits it, what history created it, and what fate awaits it, begins not with the star itself but with the darkness that concealed it for so long. The constellation Scutum does not announce itself. It sits in the summer sky of the northern hemisphere as a modest, unremarkable patch of stars, easily overlooked by casual observers who have not been told where to look. It lacks the dramatic geometry of Orion, the bright anchoring stars of Scorpius, the familiar arc of the Big Dipper. To the naked eye, Scutum offers nothing extraordinary. A faint smudge of increased stellar density, a slight brightening of the Milky Way's band in that direction. Nothing that would draw the attention of anyone not specifically searching. But point an infrared telescope towards Scutum, toward the region where the line of sight penetrates the inner spiral arms of our galaxy and drives deep toward the galactic center, and the sky transforms entirely. The stars that were invisible become visible. The clusters that were hidden behind centuries of accumulated dust resolve into dense populations of extraordinary objects. The galaxy reveals a layer of itself that optical astronomy could never access. A hidden census of stars burning in wavelengths our eyes were never built to detect. This is where Stevenson 2-18 has been waiting. Not for years, not for decades, For the entire history of human astronomical observation, from the first person who looked up and wondered what the stars were, through Galileo's first telescopic observations in 1609, through the construction of the great observatories of the 19th century, through the development of astrophysics as a quantitative science in the 20th century, this star has burned in complete obscurity, hidden not by distance alone, but by something far more effective, by the raw material of the galaxy itself, piled in layers between us, and it absorbing and scattering its light before it can complete the 20,000-year journey to our instruments. The story of how Stevenson 2-18 was finally found is a story about learning to see in a different language. In 1990, an American astronomer named Charles Bruce Stevenson was engaged in a systematic survey of infrared sources across the plane of the Milky Way. The work was methodical, cataloging, rather than discovering, in the dramatic sense, building a comprehensive inventory of objects that emitted strongly at infrared wavelengths. Stevenson's survey tools were modest by contemporary standards. The infrared detectors available in 1990 lacked the sensitivity and resolution of instruments that would come later. The computational power available for data analysis was a fraction of what modern researchers take for granted. But the survey was systematic, and systematic work across enough sky eventually finds things that targeted observations miss. Among the infrared sources Stevenson catalogued was a stellar cluster in scutum. He designated it Stevenson 2. It appeared in his catalogue as a data point among thousands, a concentration of infrared emission in a direction known for heavy dust extinction, bright enough at infrared wavelengths to merit inclusion in the catalogue, but not obviously remarkable in any other way. Stevenson noted its position and its brightness. He had no way to determine from his observations alone whether the cluster contained 10 stars or 10,000, whether its members were nearby dwarfs or distant giants, whether the infrared brightness reflected temperature, size, distance, dust reddening, or some combination of all four. He could not have known that buried within that cluster was the largest star the universe had yet revealed to human observation. The catalogue entry sat in the astronomical literature for years. Other researchers referenced it occasionally. Surveys at different wavelengths added pieces of information. The cluster accumulated data points without ever becoming the subject of intensive, dedicated study. This is the normal pace of astronomical discovery. The universe contains more objects than can be individually characterized with existing resources. Most interesting things wait in databases for years or decades before someone has both the means and the motivation to look more carefully. What changed over the following 2 decades was the technology. To understand why Stevenson 2-18 remained hidden so long and why it finally became visible, you need to understand what 20 magnitudes of visual extinction actually means in physical terms. Astronomers measure the dimming effect of interstellar dust using a unit called magnitude, a logarithmic scale inherited from ancient Greek astronomy and refined over centuries. An extinction of 1 magnitude reduces a star's apparent brightness by a factor of approximately 2.5. An extinction of 5 magnitudes reduces brightness by a factor of 100. 10 magnitudes 10,000 times fainter. 15 magnitudes 1,000,000 times fainter. 20 magnitudes. The approximate extinction between Earth and Stevenson 2, 18 inches visible wavelengths, reduces the star's optical brightness by a factor approaching 100 million. Consider what 100 million times fainter means in practical terms. Our Sun, viewed from the distance of Stevenson 2-18, would already appear as nothing more than an invisibly faint point of light. The most powerful optical telescopes ever built could not detect it from that distance without extended observation. Now take that already invisible point of light and make it 100 million times fainter still. The result is not merely undetectable. It is so far below the detection threshold of any optical instrument humans have ever constructed, or could plausibly construct, that the concept of detection becomes meaningless. Stevenson 2, 18 inches visible light is not a dim star. It is not a very dim star. It is a star whose optical emission by the time it reaches Earth has been reduced to a level that simply does not register. The dust responsible for this extinction is not concentrated in a single location. It accumulates along the entire 20,000 light-year line of sight, layer upon layer, each molecular cloud and dust lane, adding its contribution to the total obscuration. The line of sight toward the inner Milky Way, the direction in which Stevenson 2 sits, passes through multiple spiral arms. Each arm adds dust. The region near the galactic bar adds more. The inner molecular zone, the dense ring of gas and dust surrounding the galactic center, contributes still further. The result is that the most extreme stars in the galaxy, which preferentially form in the most actively star-forming regions near the galactic center, are precisely the stars most thoroughly hidden from optical observation. The galaxy conceals its most extraordinary contents behind its own structure. Infrared light behaves differently in the presence of dust, and this difference is the key to everything. The physics of the interaction between light and dust particles depends critically on the relationship between the wavelength of light and the physical size of the dust grains. Interstellar dust grains typically measure approximately 1 micrometer across, comparable to the wavelength of visible light. When radiation encounters particles of similar size, scattering occurs efficiently. The dust grains intercept visible photons, redirect them in random directions, and effectively remove them from the beam traveling toward an observer. This is the same physics that makes our sky blue shorter wavelengths of visible light scatter more efficiently off air molecules than longer wavelengths. So blue light reaches our eyes from all directions, while red light travels more directly from the sun. Infrared light has wavelengths several times longer than visible light. The same dust grains that efficiently scatter visible photons interact far less strongly with infrared radiation. The mathematical relationship between scattering efficiency and wavelength means that light at 2 micrometers in the near-infrared penetrates dust roughly 10 times more effectively than blue visible light. At longer infrared wavelengths, the penetration advantage grows further. The practical consequence for astronomy is transformative. The cosmic fog that renders Stevenson 2 to 18 completely invisible to optical telescopes becomes semi-transparent at infrared wavelengths. Not transparent. The star still appears significantly fainter in the infrared than it would without dust, but the extinction drops from 100 million times in the visible to perhaps a few times in the infrared, a difference of tens of millions. The star that cannot exist for optical astronomy becomes one of the brightest objects in the infrared sky within its wavelength range. This is why Stevenson noticed it at all. Even with the limited infrared instruments of 1990, the star's infrared brightness was sufficient to register. The dust that erased it from visible surveys only muted it slightly at the wavelength Stevenson was observing. What was invisible to every astronomer who had ever lived before the infrared era was perfectly detectable, even with early instruments, to anyone who knew where to point an infrared sensor. But detection is not characterization. Knowing that a bright infrared source exists at a certain location tells you almost nothing about the physical nature of the object producing that emission. The infrared brightness of Stevenson 2 could have indicated a relatively nearby cluster of ordinary stars, heavily reddened by dust, but not intrinsically extreme. It could have indicated a distant but unremarkable grouping. It could have hidden the most extreme stellar object in the galaxy. Without additional information, the catalog entry remained just a position and a brightness measurement insufficient to determine which of these possibilities was correct. What astronomers needed was distance. Without knowing how far away an object sits, angular size measurements cannot be converted to physical size, apparent brightness cannot be converted to intrinsic luminosity, and the physical nature of the object remains fundamentally ambiguous. Two objects can appear identical in a survey, while differing in intrinsic properties by factors of millions if one sits nearby and the other lies at vast distance. Determining distances to objects deep within the dust-obscured inner Milky Way requires techniques that themselves depend on the ability to observe the objects clearly. The primary distance method, called parallax, measures the tiny shift in a star's apparent position as Earth moves around the Sun. More distant stars show smaller shifts. By measuring this shift precisely over 6 months, astronomers can calculate distance through simple geometry. The method is elegant and direct, requiring no assumptions about the physical nature of the star. For Stevenson, 2 to 18 obscured behind 20 magnitudes of visual extinction, parallax measurements at optical wavelengths were impossible. The star was not visible to the instruments that could measure positional shifts with the necessary precision. The technique that worked beautifully for nearby stars simply could not reach through the dust to this hidden giant. This limitation persisted for more than 2 decades after Stevenson's original catalogue. The breakthrough came from 2 directions, simultaneously converging in the 2010s in a way that finally made comprehensive characterization of obscured galactic stars possible. The first direction was the development of increasingly sensitive infrared instruments capable of not merely detecting obscured stars, but measuring their properties in detail. The 2-micron all-sky survey completed in 2001 systematically mapped the entire sky at infrared wavelengths of 1, 2, 5, 1, 65, and 2.17 micrometers, providing improved brightness measurements for millions of sources, including the members of Stevenson 2. The Spitzer Space Telescope, launched in 2003, observed at mid-infrared wavelengths inaccessible from Earth's surface, revealing details about the dust emissions surrounding evolved stars and providing measurements that constrained their temperatures and luminosities more precisely. The WISE spacecraft, the Wide Field Infrared Survey Explorer, launched in 2009, added further all-sky coverage at wavelengths sensitive to the thermal emission of dusty stellar envelopes. Each successive instrument added pieces to a puzzle that only became solvable when all the pieces were available simultaneously. The second direction was the Gaia Space Observatory, launched by the European Space Agency in December 2013. Gaia represented the most ambitious astrometric mission ever attempted, designed to measure the positions and motions of approximately 2 billion stars with precision vastly exceeding anything previously achieved. By repeatedly observing the same stars over its operational lifetime, Gaia could detect the tiny parallax shifts that revealed distances even for stars embedded in the obscured inner galaxy. The spacecraft measured stellar positions to precisions approaching 10 micro-arcseconds, a unit of angle so small that it represents the apparent size of a human hair viewed from a distance of 10,000 miles. Gaia's data releases beginning in 2016 provided distance measurements for stars throughout the Milky Way at precisions that transformed our understanding of galactic structure. For the first time, astronomers could determine reliable distances to stars in the most obscured regions of the galaxy, regions that had remained unmeasured since the first telescope was pointed at the sky. When researchers combined Gaia's distance measurements with the accumulated infrared photometry from multiple surveys and applied sophisticated atmospheric models developed over decades of theoretical work, the numbers that emerged for Stevenson 2 to 18 produced a moment of disbelief that is common in science when measurements approach the boundaries of what seems physically possible. The angular diameter of the star, measured using infrared interferometric techniques that combine the light-gathering power of multiple telescopes to achieve resolution far exceeding any single instrument, combined with the distance determined from Gaia parallax measurements, produced a physical radius of approximately 2150 times the solar radius. The researchers strung the numbers. They applied different methodologies. They tested sensitivity to assumed parameters. They looked for systematic errors that might have inflated the measurement. The size remained. Different groups using different data and different analysis approaches converged on similar values. The uncertainty range spanned roughly 1800 to 2400 solar radii, depending on methodology and assumptions, but even the most conservative estimates left Stevenson 2 to 18 clearly larger than any previously measured star. This convergence of independent measurements is what separates a genuine discovery from a measurement artifact. Any single technique can produce anomalous results. Systematic errors specific to one method can mislead. But when parallax-based distances, spectroscopic temperature measurements, bolometric luminosity estimates, and angular diameter measurements all independently point toward the same extraordinary conclusion, the conclusion becomes difficult to escape. Stevenson 2 to 18 was not merely a large star, it was the largest star found in the observable universe. the star that Charles Stevenson had listed as a data point in a systematic catalogue in 1990, without any way to appreciate what that data point represented, had been hiding the current record holder for largest known stellar object within a dry clinical entry in an astronomical database. This is how science works at its most patient. The discovery was not a single dramatic moment of revelation. It was the accumulation of measurements spanning decades, each individually insufficient, collectively decisive. Stevenson catalogued la position. Subsequent surveys added brightness measurements. Theoretical models connected brightness to physical properties. New instruments provided angular sizes. Gaia provided distances. Computer algorithms integrated the data. And from this decades-long accumulation of information, a star of almost incomprehensible proportions finally revealed its true nature to the humans who had unknowingly been flying past its ancient light for the entire history of their civilization. The cluster containing this record holder deserves attention as a context for understanding what kind of stellar environment produces such extremes. Stevenson 2 is not merely a backdrop for its most famous member. It is one of the most remarkable stellar groupings in the Milky Way, a concentration of massive evolved stars that has no close analogue in well-studied nearby clusters. The cluster spans approximately 6 light-years across a diameter, roughly comparable to the distance between our Sun and Proxima Centauri, our nearest stellar neighbor. Within this volume, which would fit comfortably in the space between our solar system and the closest star in our sky, the cluster concentrates a population of stars that would be extraordinary anywhere. At least 26 confirmed red supergiant stars exist within Stevenson 2. 26. The entire cluster of astronomers studying red supergiants in the Milky Way had, before Stevenson 2 was properly characterized, gathered statistics on perhaps a few hundred such stars scattered across the galaxy. Here was a single cluster, containing dozens of them, all apparently at similar distances, all apparently at similar evolutionary stages, all formed from the same parent molecular cloud at approximately the same time. This concentration reveals something important about the timing of stellar evolution. Red supergiant stars represent a brief phase in the life cycle of massive stars. A star spends this phase bloated and cool and preparing for catastrophic death for perhaps 100,000 years out of a total lifetime measured in tens of millions of years. If you were to randomly sample the population of massive stars in the galaxy at any given moment, roughly 1 in 200 massive stars would be in the red supergiant phase. Finding 26 in a single cluster means you are observing that cluster during a very particular window of time, a few 100,000 years, when the most massive members of that cluster have all evolved off the main sequence. Simultaneously, we are observing Stevenson 2 during precisely such a window. The cluster's most massive original members formed together, perhaps 20 million years ago, burned through their hydrogen fuel over the following 10 to 15 million years, and have now simultaneously swelled into red supergiants, all caught in this brief phase before their inevitable explosions. In another million years, several will have detonated. In 10 million years, the cluster may contain no red supergiants at all, replaced instead by a collection of neutron stars and black holes embedded in expanding supernova remnants. That we happen to exist at a moment in cosmic history when this cluster is observable in this particular star sheet, and that we have developed the technology to detect it despite the obscuring dust, is a coincidence that carries its own quiet weight. The implications of Stevenson 2-18's location for its discovery timeline are worth dwelling on because they illuminate something broader about the nature of astronomical knowledge. For the entire history of naked-eye astronomy spanning thousands of years and every ancient civilization that looked up and built systems of understanding around what they saw, Stevenson 2-18 was absolutely inaccessible, not merely unresolved, not merely catalogued as a faint star, completely absent. The Babylonian astronomers who mapped the constellations, the Greek observers who built the first quantitative astronomical framework, the Islamic scholars who preserved and extended that framework through the medieval period, the European astronomers of the Renaissance who built the first telescopes, All of them lived their entire lives without any access whatsoever to the largest star in the observable universe. It did not dim in their skies. It did not appear as a faint point. It simply did not exist for them, erased by 20 magnitudes of dust. The development of infrared astronomy, a field that became scientifically productive only in the latter half of the 20th century, did not merely add new objects to an existing catalogue. It revealed an entirely different galaxy, a hidden Milky Way populated by stars, clusters, and phenomena that had been completely invisible to all previous observational modes. Stevenson 2-18 is the most extreme known example from this hidden galaxy, but it is surrounded by thousands of other massive evolved stars that were equally invisible to all previous generations and equally revealed by infrared observation. Every generation discovers that the universe contains more than the previous generation could see. The expansion of cosmic awareness is not merely the filling in of detail on an already understood map. It is the repeated discovery that the map itself was missing entire continents. Stevenson 2-18 is one of those continents, hidden, enormous, present all along, revealed only when humans learn to see in a language that dust cannot silence. The question now is not where this star is or how we found it. The question is what it actually is. What happens inside an object this extreme? What physics governs its structure, its behavior, and the violent death that awaits it in the cosmic near future? The answers begin at a level more fundamental than the star's current state. They begin with what Stevenson 2-18 was before it became what it is now, and the journey that brought it to these impossible dimensions. The first thing you need to abandon when you try to understand the interior of Stevenson 2-18 is the image of a star as a solid or liquid object. The image your mind carries, inherited from a lifetime of seeing the sun depicted as a bright sphere with a defined edge, a glowing ball suspended in blackness, is physically accurate only in the most superficial sense. The sun does have a photosphere, a layer at which its material becomes opaque enough to define something like a surface. But for Stevenson 2-18, even this qualified sense of surface dissolves into something far stranger. The boundary between star and space is not a surface, it is a gradient, a slow fading of impossibly thin material into the surrounding void, so gradual and so diffuse that the question of where the star ends and space begins has no clean answer. What exists between that uncertain boundary and the burning core is one of the most extreme structures in the known universe. Begin with the average density. Stevenson 2-18 contains somewhere between 15 and 25 solar masses of material, the uncertainty arising from how much mass the star has already shed through its intense stellar winds over its lifetime. Call it 20 solar masses as a working estimate. That is 20 times the mass of our Sun, a quantity of matter that staggers any terrestrial intuition. Our Sun alone contains 99.8% of all the mass in the solar system. 20 suns worth of material is, by any human standard, an almost incomprehensible amount. Now, distribute that mass through a volume 10 billion times larger than the Sun's volume. The average density of Stevenson 2-18 works out to approximately 1/10 of the Sun's average density. Our Sun has a mean density of roughly 1.4 grams per cubic centimeter, slightly denser than liquid water. Divide that by 10 billion, and you arrive at a number so small it requires scientific notation to express without losing the digits, approximately 0.00000014 grams per cubic centimeter, or roughly 1/10 millionth of a gram distributed through every cubic centimeter of this star's average interior. To make this concrete, consider what that density means relative to the air you are breathing right now. The air at sea level on Earth has a density of approximately 0.0013 grams per cubic centimeter. The average density of Stevenson 2-18 is roughly 10 times lower than that. The average interior of the largest known star is less dense than the air in the room where you are sitting. If you could somehow stand in the middle of this star's outer layers, you would be standing in what is, by every practical measure, a near-perfect vacuum. Better than the vacuum inside most laboratory equipment on Earth. Better than the vacuum of low Earth orbit. Yet this near vacuum glows. This near vacuum radiates energy equivalent to 440,000 suns. The paradox deserves careful attention because it reveals something fundamental about the relationship between size, temperature, and brightness. Every surface at every temperature above absolute zero radiates energy. The amount of energy radiated per unit area, per unit time, depends on the fourth power of the temperature. This relationship, known as the Stefan Boltzmann law, after the physicists who derived it in the 19th century, means that small increases in temperature produce large increases in radiated energy. Double the temperature and the radiated power per unit area increases by a factor of 16. Triple the temperature and it increases by a factor of 81. Our sun's surface burns at approximately 5778 Kelvin, is Stevenson 2-18's photosphere. The layer that defines its visible boundary reaches only about 3200 Kelvin, cool by stellar standards. In fact, 3200 Kelvin is cool enough to be called cold in stellar physics, where temperatures in stellar interiors reach millions and hundreds of millions of degrees. The surface of Stevenson 2-18 is less than 60% as hot as the surface of our Sun. By the Stefan-Boltzmann relationship, this temperature difference means that each square meter of Stevenson 2-18's surface radiates only approximately 13%, as much energy as each square meter of our Sun's surface. Per unit area, Stevenson 2-18 is actually dimmer than our Sun, and yet Stevenson 2-18 outshines our Sun by 440,000 times. The resolution of this apparent paradox lies in surface area. Volume scales with the cube of radius, but surface area scales with the square. When you increase a sphere's radius by a factor of 2150, you increase its surface area by a factor of 2150 squared, approximately 4.6 million. Stevenson 2-18 has 4.6 million times more surface area than our Sun. Even though each square meter radiates only 13% as much energy, there are 4.6 million times more square meters contributing to the total output. The net effect is a total luminosity roughly 600,000 times greater than our Sun's. This is the paradox of red supergiants. Made visible, they are simultaneously dimmer per unit area and vastly brighter in total output. A single square meter of Stevenson 2-18 surface torn free from the star and held up next to a square meter of our Sun's surface would appear notably darker. Yet the full star pours energy into surrounding space at a rate that would sterilize entire planetary systems across distances of dozens of light years. The temperature at the photosphere, 3200 Kelvin, is responsible for something that seems deeply counterintuitive. When you first encounter it, there are molecules on the surface of a star. On the surface of our Sun at 5778 Kelvin, no molecule can survive. The thermal energy available at that temperature is more than sufficient to break every molecular bond that chemistry can produce. Hydrogen molecules dissociate into individual atoms. Water molecules shatter, carbon compounds fragment. The Sun's surface is a realm of individual atoms and ions, stripped of all the chemical complexity that defines the material world of our experience. Stevenson 2-18's photosphere operates at temperatures where this is no longer true. At 3200 Kelvin, certain strongly bonded molecules can form and persist in the outer atmosphere. Titanium monoxide, a compound of titanium and oxygen atoms, forms extensively in the cool outer layers of red supergiants and produces characteristic absorption features in their spectra bands of missing light at specific wavelengths. The molecule absorbs radiation. These titanium oxide bands are in fact the primary spectroscopic signature that astronomers use to classify a star as a cool red supergiant. They are the fingerprint of a surface cool enough for simple chemistry to operate. Water vapor also forms in the outer atmospheres of the coolest red supergiants. Carbon monoxide appears. Silicon monoxide has been detected. These are not exotic or unexpected molecules. They are among the simplest compounds that form when atoms cool sufficiently to bind together. But their presence on the surface of a star, in an environment we tend to think of as defined by temperatures and energies that destroy all molecular structure, reveals how profoundly different the surface conditions of red supergiants are from the stars we typically imagine when we think of stellar physics. The titanium oxide molecules affect the color we would perceive if we could somehow see Stevenson 2-18 without the intervening dust. The absorption of certain wavelengths of visible light by these molecules, combined with the thermal emission spectrum of a 3200 Kelvin blackbody, produces the deep red color that gives red supergiants their name. The star would glow with a deep, rich crimson dimmer and more ember-like than the brilliant yellow-white of our sun, the color of cooling iron rather than the color of a nuclear furnace at full output. The structure of the interior cannot be understood without addressing convection, because convection in red supergiants operates at scales that make the convection in our sun look like ripples in a teacup. In the deep interiors of stars, energy generated by nuclear reactions travels outward primarily through radiation. Photons born in the nuclear-burning regions bounce repeatedly off electrons and atomic nuclei in a process called radiative diffusion, random walking their way outward over immense timescales. In our sun, the energy generated in the core requires approximately 1,700,000 years to reach the surface through this radiative diffusion process. The sun is essentially a leaky nuclear reactor, with energy oozing outward through an opaque plasma at a rate determined by how often photons scatter. But in the cooler outer regions of red supergiants, a different energy transport mechanism takes over. The material becomes unstable against convection. When a parcel of gas in these regions is displaced upward, it finds itself surrounded by material denser than itself, and it continues rising rather than sinking back. The result is large-scale overturning motion. Hot material from deeper layers rises, carries its thermal energy upward, cools by radiating, and sinks back down to be reheated. This is the same process occurring in a pot of water being heated on a stove, just operating at temperatures of thousands of Kelvin in a plasma hundreds of millions of miles across. The key difference between convection in our sun and convection in Stevenson 2-18 is scale. In the outermost layers of our sun, convection cells reach perhaps 1,000 kilometers across, producing the granulation pattern visible on the solar surface as a continuous churning texture of rising and sinking material. In red supergiants, the convection cells scale up with the stellar dimensions. Individual convection cells in a star like Stevenson 2-18 likely span several astronomical units, distances larger than the orbit of Jupiter, which lies more than 5 astronomical units from our sun. These are not small features on a large star. They are features comparable in scale to our entire inner solar system individual, rising and sinking columns of stellar material, each large enough to swallow the distance from the sun to beyond Jupiter. From outside, the surface of a red supergiant looks not like the smooth, uniformly bright disk of our sun, but like a small number of enormous bright patches separated by darker regions, the visible tops of these giant convection cells. Astronomers have actually imaged this surface structure on nearby red supergiants. Betelgeuse in the constellation Orion lies close enough to Earth at roughly 700 light-years that advanced interferometric techniques can resolve its disk. These images reveal exactly the large-scale, uneven brightness pattern predicted by convection models: bright regions where hot material has risen from below, darker regions where cooler material is sinking back into the interior. The features change configuration over months to years as the convective pattern evolves. For Stevenson 2-18, direct imaging of surface features remains impossible at its 20,000 light-year distance behind its curtain of dust. But the physics operating within it is the same physics visible on Betelgeuse, scaled upward by the same factor that makes Stevenson 2-18 roughly 3 times larger than its more famous cousin. The surface gravity of Stevenson 2-18 deserves separate consideration, because it determines in ways that cascade through many other stellar properties how the star behaves. Gravitational acceleration at a surface depends on the mass of the object and the distance from its center. Our sun's surface gravity measures approximately 274 meters per second, squared roughly 28 times Earth's surface gravity. An object on the Sun's surface would weigh 28 times what it weighs on Earth. But Stevenson 2-18, despite containing 20 times more mass than our Sun, spreads that mass through a radius 2150 times larger. The gravitational acceleration at its photosphere falls approximately as mass divided by radius squared. 20 solar masses divided by 2150 squared solar radii gives a surface gravity roughly 2200000 times weaker than our Sun's, perhaps 8000 times weaker than Earth's. On Stevenson 2-18, you would be effectively weightless. An object on its surface would weigh perhaps 1/100% of what it weighs on Earth. A person who weighs 75 kilograms on Earth would weigh less than 10 grams on the photosphere of this star, a weight comparable to a few pieces of paper. This near absence of surface gravity has profound consequences. It means that material near the photosphere requires almost no velocity to escape the star's gravitational pull entirely. The escape velocity from the surface of Stevenson 2-18 is roughly 20 to 30 kilometers per second, compared to 617 kilometers per second from the surface of our Sun. Material at or near the photosphere, if given even a small push by radiation pressure or convective momentum, can reach escape velocity and depart the star permanently. This ease of mass escape drives the prodigious stellar winds that continuously erode this star's outer layers at rates that would be impossible for denser, more gravitationally bound stars. Every year, Stevenson 2-18 loses an amount of mass comparable to the mass of Earth, continuously blown away from its tenuous surface by the weak gravity that barely holds those outer layers at all. Over tens of thousands of years, this mass loss removes solar masses of material from the star, gradually reducing its total mass while enriching the surrounding space with the processed elements synthesized in its interior. The pulsation of Stevenson 2-18 represents one of its most alien properties, a characteristic that makes the very question of its size at any given moment a subtle one. Red supergiants do not maintain constant dimensions. They breathe. They expand and contract over periods ranging from hundreds to thousands of days in smaller red supergiants, and over periods likely spanning years in an object as extreme as Stevenson 2-18. The mechanism driving this pulsation resembles in its basic physics the operation of a heat engine, with opacity playing the role of a valve. Opacity in this context describes how effectively stellar material blocks the passage of radiation. In certain temperature ranges, the opacity of stellar plasma changes sharply with temperature. When the outer layers of a red supergiant are compressed, they heat slightly, entering a temperature range where opacity increases. The increased opacity traps more radiation, builds up pressure, and drives the outer layers back outward. As the layers expand, they cool, moving into a temperature range where opacity decreases, radiation escapes more freely, pressure drops, and the layers begin to fall back inward. The cycle repeats, indefinitely maintained by this feedback between temperature, opacity, and radiation pressure. For Stevenson 2-18, the pulsation period is estimated at several years, driven by the star's enormous dimensions and low average density. The star is physically so large that pressure waves, which travel through the stellar material at the local sound speed, require years to cross from one side to the other. The pulsation period correlates with this sound crossing time, so a star 2150 times the Sun's diameter necessarily pulsates far more slowly than smaller variables. The amplitude of this pulsation is not trivial. During maximum expansion, Stevenson 2-18 may extend to 2200 or 2300 solar radii. During minimum, it may contract to perhaps 1900 or 2000. This variation of 10 to 15% in radius corresponds to a variation of 30 to 50% in volume. The star, in the course of a single pulsation cycle, changes its volume by an amount that itself exceeds billions of times the Sun's total volume. These pulsations ripple through the extended atmosphere, driving shocks outward through the tenuous outer layers, ejecting material into the circumstellar envelope and contributing to the already intense mass loss. Each compression sends a pressure wave outward through the stellar material, As this wave travels into regions of decreasing density, it steepens into a shock, accelerating material ahead of it to velocities that exceed the local escape velocity. The shock literally launches portions of the stellar atmosphere into space, adding episodic bursts of ejected material on top of the continuous slow wind. The circumstellar environment surrounding Stevenson 2-18, the space within a few light years of the star carved out by its intense winds and periodic ejections, preserves a record of the star's recent history in a form that infrared observations can read. As material is ejected from the star's surface, it travels outward at velocities of roughly 10 to 30 kilometers per second, carrying with it the thermal energy and chemical composition of the stellar surface at the time ejection. As this material travels away from the star and cools, it passes through temperature ranges where dust grains can condense from the gas phase. At temperatures below approximately 1500 Kelvin, silicate dust grains can form from the silicon and oxygen atoms in the ejected gas. These grains, once formed, absorb the star's radiation and are accelerated further outward by radiation pressure, dragging the surrounding gas along with them and sustaining the stellar wind through a self-reinforcing feedback. The result is a layered circumstellar envelope surrounding the star at various distances. Each layer represents a different epoch of mass loss, the distance from the star corresponding to the time elapsed since that material was ejected. Denser layers represent periods of enhanced mass loss, perhaps triggered by particularly energetic pulsation episodes or by the star passing through phases of instability in its thermal structure. Thinner regions between the dense layers represent periods of reduced ejection. By mapping this circumstellar structure at infrared wavelengths, astronomers can reconstruct something like a climate record for the star's recent history of mass loss, reading backwards through time in the outward moving shells of ejected material. The innermost regions record conditions from thousands of years ago. The outermost detectable shells record mass ejection events occurring tens of thousands of years in the past. For Stevenson 2-18, this circumstellar archaeology reveals a star that has been losing mass intensely and irregularly throughout its red supergiant phase, building up a substantial cocoon of enriched material that itself glows at infrared wavelengths. This cocoon contributes to the star's appearance in infrared surveys, making it appear even brighter than the photospheric emission alone would suggest. It is, in a sense, a star partially wrapped in its own former self, surrounded by the material it has been steadily shedding into the galaxy. The communication time across the interior of Stevenson 2-18 represents perhaps the most alien of its structural properties, the one that most thoroughly breaks any intuition derived from objects on human scales. Sound travels through stellar material at velocities determined by the temperature and density of that material. In the outer layers of Stevenson 2-18, where temperatures hover around a few thousand Kelvin and densities approach near vacuum, sound travels at velocities of a few kilometers per second. Given the star's diameter of approximately 1.86 billion miles, a sound wave generated at the photosphere on one side of the star would require roughly a decade to reach the photosphere on the opposite side. Information about disturbances, about changes in pressure or temperature or composition, travels across this star at a rate that makes the star effectively disconnected from itself. The outer layers of Stevenson 2-18 do not know on any timescale relevant to human observation what is happening in its core. When a convective cell rises on one side of the star and alters the local pressure distribution at the photosphere, it takes years for that pressure disturbance to propagate even partially around the star. The opposite side of the photosphere responds to conditions from years ago. Different regions of the photosphere are, in a real physical sense, causally isolated from each other on timescales of months to a few years. This isolation gives the star its chaotic asymmetric appearance when compared to smaller, more coherent objects. Our Sun, with a sound crossing time of only a few hours, maintains a relatively uniform photosphere because disturbances propagate quickly and equilibrate. Red supergiants with sound crossing times of years develop and maintain enormous structural asymmetries because different regions evolve quasi-independently. The star is too large to maintain the coordinated behavior that characterizes smaller, faster communicating objects. In this sense, Stevenson 2-18 is not simply a large star. It is a fundamentally different kind of object, one whose scale has crossed thresholds where the properties we associate with stars' coherence, regularity, defined boundaries, steady energy output begin to break down. It is a star approaching the limit of what stellar physics can maintain a near vacuum, occupying a volume that dwarfs planetary systems, held together by the continuous flow of energy from nuclear reactions far below and the weak gravitational pull of its own diffuse mass. That it holds together at all is remarkable. That it can reach these dimensions while remaining recognizably a star, rather than dispersing entirely into the surrounding interstellar medium, speaks to the extraordinary balancing act that stellar physics performs even at its most extreme limits. The question of how Stevenson 2-18 arrived at this extreme configuration, what history produced this particular object in this particular state, requires going back much further than the red supergiant phase. It requires returning to the moment roughly 20 million years ago, when none of this yet existed, when the material that would eventually become the largest known star was still part of a cold, dark cloud of gas and dust, drifting through the inner spiral arm of a young galaxy, waiting for the gravitational trigger that would begin the long transformation into something extraordinary. 20 million years ago, the material that would become Stevenson 2-18 did not exist as a star. It existed as coldness, as stillness, as a region within a molecular cloud drifting through the inner spiral arm of the Milky Way, a vast dark accumulation of hydrogen and helium gas, seeded with trace amounts of heavier elements, dust, grains, and simple molecules. The temperature of this cloud hovered near 10 Kelvin, just 10 degrees above absolute zero. Cold enough that atoms moved with almost no thermal energy, cold enough that the cloud could persist for millions of years without collapsing under its own gravity, held up by the gentle pressure of its own slight warmth and the magnetic fields threading through it. Nothing about this cloud viewed from the outside would have suggested it was about to produce the largest star in the observable universe. What broke the equilibrium is uncertain. It may have been the shock wave from a nearby supernova, a pressure pulse from an exploding massive star that compressed the cloud beyond the threshold where gravity could overcome the resisting forces. It may have been the passage of the cloud through a spiral arm density wave, the gravitational enhancement that sweeps through the disk of the galaxy over millions of years, periodically compressing the interstellar medium into configurations that trigger star formation. It may have been the collision of two smaller cloud fragments, their combined mass exceeding the critical threshold for gravitational collapse. Whatever the trigger, the collapse began, and once begun, it could not be stopped. The collapse of a molecular cloud into stars is not a gentle process. It is not the orderly condensation of a smooth sphere shrinking uniformly toward its center. It is chaotic, hierarchical, and violent. The cloud fragments as it falls, different regions collapsing faster than others, forming filaments and sheets and knots of denser material. Within these knots, smaller fragments collapse further. The hierarchy continues down through scales until individual protostellar cores form, each accumulating mass from the surrounding gas through their own gravitational attraction. The material that would eventually become Stevenson 2-18 collapsed into one of the most massive of these protostellar cores. From the beginning, the amount of gas falling inward toward this particular center was exceptional. The protostar grew, rapidly accumulating mass from a large reservoir of infalling material, its gravitational pull strengthening with each additional solar mass of gas it incorporated. As material fell inward, gravitational potential energy converted to thermal energy. The protostellar core heated. The infalling gas compressed under its own weight, raising temperatures and densities toward the conditions required for nuclear reactions. When the core temperature reached approximately 10 million Kelvin, hydrogen nuclei began fusing into helium. The nuclear furnace ignited. The star was born. In this early configuration, before any significant evolution had occurred, the young Stevenson 2-18 was not the bloated, cool, diffuse object we observe today. It was its opposite in nearly every measurable way. Compact, dense, extraordinarily hot, radiating primarily in ultraviolet wavelengths invisible to human eyes. Surface temperatures exceeded 20,000 Kelvin, more than 3 times hotter than our Sun's surface. The young star shone with an intensity already exceeding tens of thousands of solar luminosities, making it one of the most visually dramatic objects in its region of the galaxy from the moment of its birth. Its diameter at this early stage, the so-called zero-age main sequence phase, when a star first begins stable hydrogen burning, spanned perhaps 10 to 15 solar radii. Not the billions of miles it occupies today, but merely 10 to 15 times the diameter of our Sun. Enormous by human standards, but compact by the standards of what this star would eventually become. This transformation from compact blue supergiant to extended red supergiant, from a diameter of 15 solar radii to a diameter of 2,150, from a surface temperature of 20,000 Kelvin to 3,200, would require millions of years and would pass through phases of stellar evolution that fundamentally restructure the star's interior architecture. The fuel that powered this young star was hydrogen, the most abundant element in the universe, constituting approximately 75% of all normal matter by mass. In the core of the young Stevenson, 2 to 18 temperatures and densities were sufficient to drive hydrogen fusion at a rate that our Sun cannot approach. The mechanism was not the same chain of reactions that powers our Sun. In stars of modest mass like our Sun, hydrogen fuses primarily through what physicists call the proton-proton chain. 2 hydrogen nuclei, each consisting of a single proton, collide with sufficient energy to overcome their mutual electromagnetic repulsion and fuse, releasing energy through a series of steps that ultimately produce one helium nucleus, 4 hydrogen nuclei. The proton-proton chain operates at relatively modest core temperatures, igniting at about 10 million Kelvin, and proceeds slowly enough that our Sun will burn through its hydrogen supply over 10 billion years. In the hot, dense core of a star like the young Stevenson 2 to 18, a different mechanism dominated. The carbon-nitrogen-oxygen cycle, abbreviated as the CNO cycle, uses carbon, nitrogen, and oxygen nuclei as catalysts in a sequence of reactions that ultimately converts 4 hydrogen nuclei into 1 helium nucleus while regenerating the original catalyst nuclei. The net result is the same as the proton-proton chain. 4 hydrogens become 1 helium and energy is released. But the CNO cycle operates far more rapidly at high temperatures. Here is the crucial difference. The proton-proton chain's rate increases approximately with the 4th power of temperature. The CNO cycle's rate increases approximately with the 16th power of temperature. This extraordinary sensitivity means that small increases in core temperature produce enormous increases in energy generation through the CNO cycle. The core of a young, massive star, compressed by the weight of 20 or more solar masses above it, reaches temperatures of 40 to 50 million Kelvin, 3 to 4 times hotter than our Sun's core. The CNO cycle at those temperatures burns hydrogen at a rate millions of times faster per unit mass than the proton-proton chain in our Sun. This rate difference explains the apparent paradox of stellar lifetimes. You might expect a star with 20 times more fuel than our Sun to live 20 times longer. Instead, it lives 1,000 times shorter. The young Stevenson 2 to 18 burned through its core hydrogen supply not over billions of years, but over roughly 10 to 15 million years. A period that would span the entire history of our genus Homo, from our earliest ancestors to the present day, is less than the time this star spent simply burning hydrogen in its core before its real evolutionary drama began. For those 10 to 15 million years, the young Stevenson 2 to 18 existed in a state of dynamic equilibrium between 2 forces that governed every second of its existence. Gravity pulled every atom in the star toward every other atom, an inexorable inward force that would, if unopposed, collapse the entire star into a black hole in less than an hour. The mathematics of free fall under gravity is unambiguous. A star the size of our Sun, if stripped of all internal pressure support, would collapse to a point in approximately 25 minutes. For a star 20 times more massive, the collapse would be proportionally faster. Nothing in the star's structure, no strength of material, No chemical bonds, no electromagnetic forces between atoms could resist this gravitational pull on its own. What opposed gravity was radiation pressure. The nuclear reactions in the core converted a small fraction of the fusing hydrogen's mass directly into energy, following Einstein's relationship between mass and energy. This energy, born as gamma-ray photons deep in the core, began the long journey outward through the stellar interior, bouncing repeatedly off electrons and nuclei in a process of radiative diffusion that would take tens of thousands of years to complete. As these photons pushed outward through the stellar material, they exerted pressure on that material. Radiation pressure directed outward from the energy-generating core exactly balanced the inward gravitational force. This balance, called hydrostatic equilibrium, is not static. It is a continuous dynamic adjustment, like a thermostat maintaining temperature by cycling a furnace on and off. If the star were somehow compressed slightly, the core temperature would rise, nuclear reactions would accelerate, radiation pressure would increase, and the star would expand back toward equilibrium. If the star was somehow expanded slightly, the core would cool, reactions would slow, radiation pressure would drop, and gravity would contract the star back toward equilibrium. The feedback is self-correcting, maintaining the star at the size and temperature at which these two forces balance. This equilibrium persisted with extraordinary stability for 10 to 15 million years. The star shone with fierce blue-white light, shedding enormous quantities of radiation into the surrounding galaxy, and processed its hydrogen fuel with the relentless efficiency of the CNO cycle. But hydrogen cannot last forever, even in a star this massive. The depletion of hydrogen in the core was not sudden. It was gradual, occurring over millions of years, as the CNO cycle converted hydrogen nuclei into helium nuclei faster than fresh hydrogen could be mixed in from surrounding regions. As helium accumulated in the core, the fraction of hydrogen available for fusion declined. The nuclear energy generation rate began to drop. The radiation pressure that had held the star up against gravity began to weaken. The star responded to this weakening by contracting slightly, compressing the core under its own weight. This compression raised the core temperature and restored the fusion rate temporarily. But the core was now burning through a shrinking hydrogen supply at an accelerating rate, the increased temperature speeding the CNO cycle further. The end of core hydrogen burning approached with increasing speed as depletion accelerated. When core hydrogen was finally exhausted, perhaps 15 million years into the star's life, the equilibrium broke catastrophically. The core, now composed primarily of helium ash with no energy source to maintain pressure, began to contract under gravity. The contraction released gravitational potential energy, as heat warming the surrounding layers. A thin shell of hydrogen just outside the exhausted core, heated by this energy flow, reached temperatures sufficient to ignite. The CNO cycle reignited not in the core, but in a thin shell surrounding it. This shell burning produced more energy than the previous core burning had. The outer layers of the star responded to this increased energy flow by expanding. The surface moved outward. As the surface moved away from the hot interior, it cooled. The star began to swell and redden simultaneously, its surface expanding while its temperature dropped. This expansion represents the transition from blue supergiant to red supergiant, a transformation that unfolded over perhaps a few tens of thousands of years. Brief by stellar standards, longer than all of human recorded history. The physics driving this expansion requires understanding something subtle about how energy moves through stellar interiors at different temperatures. In the hot, dense inner regions of a star, energy travels outward primarily through radiation. Photons bounce off electrons and nuclei, gradually diffusing outward in a random walk that requires tens of thousands of years to complete. This radiative transport is relatively efficient in hot, ionized plasma, where photon mean free paths, while short allows steady outward energy flow. But in the cooler, outer regions of an expanding star, the character of the plasma changes. At temperatures below roughly 10,000 Kelvin, hydrogen begins to recombine, capturing electrons to form neutral atoms. Neutral hydrogen absorbs radiation far more efficiently than ionized hydrogen, dramatically increasing the opacity of the stellar material. When opacity increases, radiation cannot diffuse outward as efficiently. Energy piles up in these outer layers, and the plasma becomes convectively unstable. Convective instability means that a parcel of gas displaced upward will find itself lighter than its surroundings and will continue rising rather than returning to its original position. Large-scale overturning motions develop with hot material rising and cool material sinking in a circulation that transports energy far more efficiently than radiation in these opaque outer layers. The transition from radiative to convective energy transport restructures the star's outer architecture. Crucially, convective envelopes have a different response to increased energy input than radiative zones. When more energy flows into the base of a convective envelope, the envelope expands outward rather than simply heating up. The convective circulation adjusts to carry the increased energy flux, and the star responds by growing larger rather than hotter. This is the fundamental reason red supergiants expand to such extreme dimensions. Their outer convective envelopes absorb the increased energy output from shell burning and respond by expanding enormously, spreading their surfaces over ever larger areas. The expansion is not limited by any hard physical boundary. It continues until a new equilibrium is reached, with energy generated in the burning shells transported outward through the convective envelope and radiated into space from the cool, extended surface. For a star with 20 solar masses and an active hydrogen-burning shell surrounding a contracting helium core, this new equilibrium occurs at dimensions measured in hundreds or thousands of solar radii. The specific mass range that produces the largest red supergiants, the range within which Stevenson 2-18 sits, deserves careful attention because it reveals why this particular star, rather than something more massive, holds the size record. Consider what happens to stars significantly more massive than Stevenson 2-18. Stars born with initial masses of 50-100 or more solar masses face a qualitatively different evolutionary challenge. Their luminosities are so extreme, their radiation pressures so intense, that the radiation-driven stellar winds that all massive stars experience become catastrophically powerful. These winds, driven by the absorption of photons in the spectral lines of heavy elements in the stellar atmosphere, can carry away the hydrogen envelope entirely before the star has time to expand into a red supergiant configuration. A star born with 100 solar masses begins its life with a luminosity approaching several million times our sun's output. The radiation pressure this luminosity exerts on the stellar atmosphere, particularly on atoms and ions with strong absorption features in the ultraviolet, drives mass loss rates that can strip the hydrogen envelope from the star within a few million years. Without a hydrogen envelope, the expanding phase that produces red supergiants cannot occur. The star never develops the extended outer layers that define this class. Instead, these most massive stars become Wolf-Rayet objects, stars that have lost their hydrogen envelopes entirely and expose their hot, compact helium cores to direct observation. Wolf-Rayet stars are not large. They typically measure only a few solar radii, across compact and dense and blindingly luminous, radiating primarily in ultraviolet wavelengths that would be lethal to any unprotected biology in their vicinity. They are the stripped-down cores of stars that could have become red supergiants, but lost their outer layers before the expansion could occur. The sweet spot for maximum red supergiant dimensions lies in the range where stars retain their hydrogen envelopes through the transition to shell burning, expanding to extreme dimensions before mass loss has time to remove the envelope. Stars in the range of approximately 20 to 40 solar masses thread this needle. They lose mass through stellar winds, but not fast enough to shed their envelopes entirely before the convective expansion proceeds. They become true red supergiants, developing the enormous extended configurations that make objects like Stevenson 2-18 possible. Stars below this range, with initial masses between roughly 8 and 20 solar masses, also become red supergiants, but their lower luminosities and lower mass loss rates tend to produce more modest dimensions, rarely exceeding 800 to 1,000 solar radii. The greater mass of the 20 to 40 solar mass range drives more energetic shell burning, which powers more extreme envelope expansion, which produces the record-breaking dimensions we observe in Stevenson 2-18. This mass dependence on maximum size is not a smooth monotonic relationship. It has an optimum, a sweet spot, beyond which increasing mass actually decreases maximum red supergiant dimensions because mass loss begins to dominate before the expansion can proceed to its limit. Stevenson 2 to 18 at an initial mass of roughly 25 to 40 solar masses apparently sits near or within this optimal range, having retained enough of its hydrogen envelope to expand fully while still losing enough mass to settle into a structure near the theoretical maximum for red supergiant dimensions. The helium core that accumulated during the main sequence phase, the ash of hydrogen burning that could not sustain the star against gravity, did not remain inert forever. As the outer layers expanded and the star transitioned to red supergiant status, the helium core continued to contract under gravity heating as gravitational potential energy converted to thermal energy. When the core temperature reached approximately 100 million Kelvin, a new burning phase ignited. Helium fusion, unlike hydrogen fusion, requires this much higher ignition temperature because helium nuclei carry twice the positive charge of hydrogen nuclei. Two positively charged particles repel each other electromagnetically, and helium nuclei with their double charge repel more strongly than hydrogen nuclei. Higher temperatures provide the kinetic energy needed to force helium nuclei close enough for the strong nuclear force to take over and fuse them. The process by which helium fuses is called the triple alpha process, a name that refers to alpha particles, the physics term for helium nuclei. Two helium nuclei collide and briefly form a beryllium-8 nucleus, an unstable intermediate that normally decays back into two helium nuclei within less than 1/10,000th of a trillionth of a second. At the temperatures and densities prevailing in the helium-burning core, a third helium nucleus strikes this fleeting beryllium nucleus before it can decay, producing stable carbon, 1,2, and releasing energy. This reaction was a near miss in the history of carbon-based life. Fred Hoyle, the British astronomer and cosmologist, realized in the 1950s that the triple alpha process would be far too slow to produce the observed cosmic abundance of carbon unless the carbon 1,2 nucleus possessed a specific excited energy state called a resonance that enhanced the reaction rate at stellar temperatures. He predicted this resonance before it was measured on the grounds that we exist and are made of carbon, and therefore the universe must be able to produce carbon in abundance. The resonance was subsequently found exactly where he predicted it. The carbon in your body exists because the energy levels of carbon 1,2 nuclei happen to have precisely the right values to make the triple alpha process efficient at stellar core temperatures. The helium burning phase in Stevenson 2 to 18's core lasted perhaps 1 million years short by comparison with the 10 to 15 million year hydrogen burning phase, because helium fusion releases less energy per unit mass than hydrogen fusion. The core converted helium into carbon and oxygen, with the ratio of products depending on the competition between the triple alpha process and a secondary reaction that converts carbon into oxygen by capturing a fourth helium nucleus. When helium was exhausted, a carbon-oxygen core remained surrounded by a helium-burning shell, which was itself surrounded by the hydrogen-burning shell, all embedded within the enormous convective envelope extending to the distant photosphere. The star had become structurally something like a cosmic onion, layer upon layer of burning shells surrounding an inert core, each layer processing the ash of the layer above into heavier elements. The entire complex structure maintained by the energy output of these nested burning zones flowing outward through the convective envelope and ultimately escaping into space as the dim red light we detect with infrared telescopes 20,000 light-years away. Each subsequent burning phase, carbon igniting at 500 million Kelvin, neon at 1 billion Kelvin, oxygen at 2 billion, silicon at 3 billion, proceeded faster than the last. Carbon burning lasted perhaps 1,000 years, neon burning just a few years, oxygen burning mere months, silicon burning, the final stage that converts the last available fuel into iron, completes in days. As these burning phases accelerate toward their conclusion, Stevenson 2 to 18 races toward a destiny It has been approaching since the moment of its formation. The iron that accumulates in its core is not merely another element, it is the end of the road, the final product, the ash from which no further energy can be extracted. And when enough iron accumulates, the story of the largest known star will enter its final chapter, a chapter that unfolds not over millions of years or thousands or even hours, but in the time it takes you to draw a single breath. The contest for the title of largest known star has a history that reveals as much about the limits of measurement as it does about the limits of stellar physics. For most of the 20th century, the question was not even meaningfully askable. The tools required to determine stellar radii with sufficient precision for distant obscured objects simply did not exist. Astronomers could estimate sizes for nearby stars using angular diameter measurements, but the sample of stars with reliably determined physical dimensions remained small, biased toward objects close enough and bright enough to be accessible to available instruments. As technology improved through the late 20th and early 21st centuries, the catalogue of measured stellar radii expanded. With expansion came competition. Several red supergiants emerged as candidates for the largest known stellar object, each holding or contesting the record, as successive measurements refined the picture. Understanding why Stevenson 2-18 now sits at the top of this list, and why that position is secure rather than provisional, requires examining what happened to the competitors. VY Canis Majoris held the popular imagination's version of the record for much of the early 2000s. Located approximately 3900 light-years from Earth in the constellation Canis Major VY. Canis Majoris was close enough to study in considerable detail, and what astronomers found was extraordinary. The star displayed one of the most dramatic circumstellar environments ever observed, surrounded by complex structures of ejected material, including arcs, knots, and filaments of gas and dust, extending across distances of light years. These structures testified to a history of intense, irregular mass loss, with the star having shed enormous quantities of material in discrete events over the past few thousand years. Early size estimates for VY Canis Majoris derived from angular diameter measurements, combined with distance estimates available before Gaia suggested dimensions of 1800 to 2000 solar radii. These numbers appeared in textbooks, in documentary films, in popular science articles, establishing VY Canis Majoris in the public consciousness as the largest known star. The designation seemed secure. Then the measurements were revised. The Gaia spacecraft's precise parallax measurements, released beginning in 2016, provided distance determinations for stars throughout the Milky Way that were simply more reliable than anything previously available. For VY Canis Majoris, Gaia's distance measurement came out somewhat smaller than the pre-Gaia estimates. When a star turns out to be closer than previously thought, its calculated physical size must be revised downward, since the same angular diameter corresponds to a smaller physical diameter at a closer distance. The revised distance, combined with updated angular diameter measurements and improved atmospheric modeling, reduced VY Canis Majoris to approximately 1400 to 1500 solar radii. Still an object of extraordinary dimensions, still one of the largest stars known, still a monster that would swallow the inner solar system if placed at our sun's position, but clearly and significantly smaller than the central estimates for Stevenson 2-18. The revision illustrates a fundamental challenge in measuring stellar sizes. Every step in the calculation chain carries uncertainty. The angular diameter measurement depends on the resolution and calibration of the interferometric instrument used to make it. The distance measurement depends on the precision of parallax observations and the corrections applied for various systematic effects. The conversion from angular to physical diameter depends on both of these. And all size measurements for red supergiants carry the additional complication that these stars are variable objects without sharp boundaries, pulsating over years and fading gradually into circumstellar envelopes that blend continuously with the surrounding interstellar medium. The history of VY Canis Majoris's revised size estimate is not a story of error. It is a story of increasing precision of measurements being refined as better tools became available. The same process that demoted VY Canis Majoris Elevated Stevenson 2 to 18 as Gaia's distance measurements and improved infrared interferometry converged on dimensions that exceeded 2,000 solar radii. Scuti presented a different kind of challenge to the record-keeping, located approximately 5700 light-years from Earth, also in the constellation Scutum, and relatively close in the sky to Stevenson 2 itself. Scuti was identified as a potential record holder based on early estimates, suggesting dimensions approaching or possibly exceeding 2,000 solar radii. For a period, various sources cited Scuti as the largest known star, the same title now held by Stevenson 2 to 18. The measurement history of Scuti reveals the same pattern as VY Canis Majoris, but with added complexity from the star's extreme variability. Scuti is classified as a semi-regular variable, pulsating with a primary period of approximately 740 days, but with significant irregularity overlaid on this basic periodicity. The star's radius changes substantially over its pulsation cycle, expanding and contracting by amounts that affect size determinations depending on when observations are made. Measuring the radius of a pulsating star at maximum expansion produces a different number than measuring it at minimum, and both are legitimately the star's radius at that moment. Gaia's distance measurements placed Scuti at a distance somewhat different from earlier estimates, and the resulting recalculations of physical size settled on values around 1700 solar radii as the most reliable current estimate. Again, the revision was not a correction of a previous error, but a refinement made possible by improved measurement technology. And again, the result was a star clearly smaller than Stevenson 2 to 18, when both are measured with the best available tools. NML Cygni remains a genuine competitor, in a way that the revised estimates of VY Canis Majoris and Scuti no longer do, located approximately 5300 light-years from Earth. In the constellation Cygnus NML, Cygni is a red supergiant with properties that place it among the most extreme stars in the Milky Way. Its luminosity rivals Stevenson 2 to 18's, estimated at roughly 27000 to 300,000 solar luminosities. Its mass loss rate is extraordinary, among the highest measured for any red supergiant. Its circumstellar environment is rich and complex. Size estimates for NML Cygni span a wide range in the literature, from roughly 1400 to perhaps 2000 solar radii, depending on methodology and assumptions. Some measurements hint at dimensions approaching Stevenson 2 to 18 scale. The uncertainty in NML Cygni's size is large enough that the relative ranking between these two stars cannot be definitively resolved with current measurements. Technical specialists in stellar astrophysics acknowledge this ambiguity, which is why the description of Stevenson 2 to 18 as the largest known star carries the qualifier known rather than the unhedged assertion of record. What distinguishes Stevenson 2 to 18 from NML Cygni in the current consensus is not that its size is more precisely measured, because both carry substantial uncertainty, but that the central estimates for Stevenson 2 to 18 consistently emerge above 2000 solar radii in multiple independent analyses, while NML Cygni's central estimates tend to fall below that threshold. When the uncertainties of both stars are compared, Stevenson 2 to 18 occupies the higher position in the distribution. The record is real, but it sits within ranges that honest scientists hold with appropriate tentativeness. Understanding why any star can reach dimensions of 2000 solar radii and why nothing dramatically larger has been found requires confronting a fundamental physical limit that operates not during the red supergiant phase but much earlier, at the moment of stellar birth. Every star faces a maximum possible mass determined by the competition between the gravity drawing material inward during formation and the radiation pressure from the growing protostar pushing material outward. As a protostellar core accumulates mass from its surrounding cloud, its luminosity increases rapidly. The mass-luminosity relationship for massive stars is steep, with luminosity scaling approximately as the third or fourth power of mass. Double the mass, and the luminosity increases by a factor of 8 to 16. This steep scaling means that as a forming star grows more massive, its radiation output increases far faster than its gravitational pull on surrounding material. Eventually, for the most massive forming stars, the radiation pressure from the protostellar surface equals and then exceeds the gravitational force, pulling in fresh material from the surrounding cloud. Further accretion becomes impossible. The forming star has reached what is called the Eddington limit, the point at which radiation pressure precisely balances gravity for infalling material. The protostar essentially blows away its own food supply, halting growth at a mass determined by the Eddington balance. For stars forming in gas with typical heavy element abundances similar to our Sun's, this limit falls somewhere between 150 and 300 solar masses. Stars more massive than this cannot form through the normal process of accretion from a parent cloud. They could only potentially arise through the merger of already formed massive stars in dense cluster environments, a process that may occur occasionally in the most extreme star-forming regions, but is rare. The most massive stars ever confirmed objects like R136 are one in the Large Magellanic Cloud, weighing in at perhaps 200 to 300 solar masses, approach this formation limit. They exist as compact, blindingly luminous blue objects, not as extended red supergiants. Their enormous mass loss rates prevent them from ever expanding to the dimensions of a Stevenson 2 to 18. The upper size limit for red supergiants specifically arises from a different set of constraints than the upper mass limit for stellar formation. These are separate physical questions with separate answers, and confusing them produces a confused picture of what determines maximum stellar dimensions. The maximum size of a red supergiant is set by the balance between three factors: the energy output of the nuclear burning shells, driving the envelope expansion, the opacity of the envelope material, determining how that energy moves outward, and the mass loss rate at the surface, determining how quickly the envelope is eroded. All three factors depend on stellar mass in ways that produce an optimal mass range for maximum expansion. Theoretical models of stellar structure, the same sophisticated computer codes that trace stellar evolution from birth through death, by numerically solving the equations governing pressure, temperature, composition, and energy transport at every layer within the star, predict maximum red supergiant radii in the range of approximately 2000 to 3000 solar radii. The precise upper limit depends on assumptions about mass loss rates, which remain among the most uncertain parameters in stellar evolution theory. Mass loss rates for red supergiants are notoriously difficult to calculate from first principles. They depend on the dynamics of the extended atmosphere, the formation and acceleration of dust grains, the coupling between dust and gas, the effects of pulsation on atmospheric structure, and the geometry of the mass outflow. These processes interact in complex, non-linear ways that current theoretical models cannot fully capture. Empirical estimates of mass loss rates, derived from observations of circumstellar envelopes, carry uncertainties of factors of several. This uncertainty in mass loss rates propagates directly into uncertainty in predicted maximum stellar sizes. If mass loss rates are lower than assumed, stars can retain their envelopes longer and expand to larger dimensions before the envelope is eroded away. If mass loss rates are higher, envelopes are stripped faster and maximum expansion is curtailed. The fact that Stevenson 2 to 18 measures approximately 2150 solar radii sits comfortably within the range of theoretical predictions while approaching their upper boundary. The star is extreme, but not inexplicably so. It falls within what stellar physics allows near the upper edge of the permitted range. Whether anything larger than Stevenson 2 to 18 exists in the observable universe is a question that current data cannot definitively answer, and the honest acknowledgement of this uncertainty reveals something important about the nature of astronomical knowledge. The Milky Way contains approximately 400 billion stars. Of these, perhaps a billion exceed the minimum mass of roughly 8 solar masses required to eventually pass through the red supergiant phase. At any given moment, roughly 1 in 200 of these massive stars exists in the red supergiant phase, given the phase duration of approximately 100,000 years, compared to total stellar lifetimes of tens of millions of years. This suggests that several million red supergiants currently populate our galaxy. Of these several million red supergiants, we have measured the physical radii of perhaps a few thousand, with sufficient precision to place them meaningfully in size rankings. This represents well under 1% of the estimated red supergiant population. The fraction of the distribution we have sampled is so small that statistical arguments cannot rule out the existence of larger stars lurking in the unmeasured majority. The regions of the galaxy most likely to harbor the most extreme red supergiants are also the regions most difficult to observe. The inner spiral arms, the regions surrounding the galactic bar, the inner molecular zone, closer to the galactic center, all these environments are more actively star-forming than the solar neighborhood and therefore contain higher proportions of massive young stars in various evolutionary stages. They are also the most heavily obscured by dust, the most difficult to survey systematically, and the least thoroughly characterized. Stevenson 2-18 was itself hidden in one of these obscured inner galaxy regions, revealed only by the combination of infrared surveys and Gaia parallax measurements that matured in the 2010s. The same combination of capabilities that revealed Stevenson 2-18 is now being applied to other obscured stellar populations. Each new survey potentially discovers additional extreme objects. Each refined measurement potentially revises size rankings. The next generation of observational facilities will extend this survey reach dramatically. The extremely large telescope, under construction at Cerro Armazones in the Atacama Desert of Chile, will feature a primary mirror 39 meters in diameter when completed, making it roughly 4 times the diameter of the largest telescopes currently operating. Its enormous light-gathering area, combined with adaptive optics, systems that correct in real time for the blurring effects of Earth's atmosphere, will achieve angular resolutions approaching those of the Hubble Space Telescope, but with far greater sensitivity to faint objects. At infrared wavelengths, the extremely large telescope will be able to resolve and characterize stellar populations in deeply obscured regions of the Milky Way that no current facility can access. The dust extinction that hides Stevenson 18 inches optical wavelengths, while still significant at near-infrared wavelengths, becomes increasingly transparent at the mid-infrared wavelengths, accessible to the ELT's instrument suite. Stars hidden behind even greater extinctions than Stevenson 2-18 will become characterizable. The giant Magellan telescope, also under construction in Chile, will combine 7 individual mirror segments into an effective collecting area corresponding to a 25-meter primary. The 30-meter telescope planned for either Hawaii or the Canary Islands will provide comparable capabilities in the Northern Hemisphere. Together, these 3 facilities will transform our census of extreme stellar objects throughout the galaxy during the 2030s and beyond. Space-based capabilities will complement ground-based surveys. The James Webb Space Telescope, now operational, is providing unprecedented infrared sensitivity from its position beyond Earth's atmosphere, free from the water vapor absorption that limits certain infrared wavelength ranges from the ground. While Webb's primary scientific missions focus on distant galaxies and exoplanet atmospheres, its capabilities extend naturally to the study of obscured Milky Way stellar populations. The Nancy Grace Roman Space Telescope, planned for launch in the late 2020s, will combine Webb-like infrared sensitivity with a field of view approximately 100 times wider than Webb's. This wide-field capability makes Roman ideal for discovering rare objects scattered across large areas of sky, including extreme red supergiants that might exist anywhere within the survey volume. Roman's systematic survey of obscured galactic regions will provide a census of extreme stellar objects far more complete than anything currently available. The statistical question of whether Stevenson 2-18 sits near the true physical upper limit or merely near the top of an incompletely sampled distribution will be answered over the coming decades as these facilities accumulate data. If surveys of previously uncharacterized obscured regions discover multiple stars larger than Stevenson 2-18, that would indicate we have been missing the true extremes of the distribution, and the record is likely to be broken. Repeatedly, if expanded surveys find nothing larger, despite characterizing hundreds of thousands of additional red supergiants, that would suggest Stevenson 2-18 sits genuinely near the physical maximum that stellar physics permits. Either outcome advances understanding, either the record falls demonstrating the universe is even more extreme than our current measurements show, or it stands revealing that we have found the true boundary of what stars can become. Both possibilities carry their own form of significance. What the current measurements establish beyond reasonable doubt is that Stevenson 2-18 at approximately 2150 solar radii represents an extreme of natural organization that the universe actually produces. This is not a theoretical prediction, not a computer model extrapolation, not a speculation about what might exist in unexplored regions. It is a measurement made by instruments operating at the limits of human technological capability, confirmed by multiple independent methodologies, situated within a theoretical framework that both predicted and now validates the possibility of such extreme dimensions. The universe permits stars this large. We know this because one actually exists, and it has been burning invisible to us 20,000 light-years away for the entire history of human astronomical observation. Its secrets finally yielded, not to the naked eye that catalogued the constellations, not to the optical telescopes that revealed the structure of the galaxy, but to the infrared instruments that learned to read the universe in a language that dust cannot erase. What those instruments also tell us with increasing clarity is that the time remaining in Stevenson 2-18's story is short by cosmic standards. The star that took 20 million years to reach its current state of extreme expansion is now racing through its final evolutionary stages at a pace that compresses millions of years of earlier history into intervals measured in thousands, hundreds or mere days. The core that spent 15 million years burning hydrogen has long since moved on. The helium that replaced it burned out in 1 million. The carbon took 1,000 years, the neon a few, the oxygen months. The iron is accumulating now. Or it accumulated already, and we simply do not yet know. The end is either imminent or it has already happened, and the light telling us so has not yet completed its 20,000-year journey to reach us. Iron is the end of everything a star can do. Not because iron is rare, not because iron is inert in ordinary chemical terms, but because of where iron sits on a curve that governs the energy landscape of all atomic nuclei, a curve that determines which nuclear reactions release energy and which ones consume it. Every element lighter than iron releases energy when its nuclei fuse together. This is why stars shine. Hydrogen fusing into helium, helium into carbon, carbon into oxygen, oxygen into silicon, silicon into iron. Each step releases the energy that supports the star against its own gravity. Each step sustains the equilibrium that allows a star to exist as a stable, energy-radiating object, rather than a collapsing ball of matter falling into itself. Iron sits at the peak of this curve. Iron, 5-6, the most common iron isotope, has the highest binding energy per nucleon of any nucleus in the periodic table. This means it is the most tightly bound configuration of protons and neutrons that exists. Fusing iron into heavier elements does not release energy, it requires energy. The nuclear bookkeeping that has sustained Stevenson 2-18 for 20 million years simply stops working when the fuel reaches iron. The furnace has been running on progressively less efficient fuels each burning phase, shorter and hotter than the last, and now it has reached a fuel that will not burn at all. The iron accumulates in the core like unpayable debt. Each day of silicon burning deposits roughly 1/10 of a solar mass of iron into the core. The iron sits there, inert, contributing its weight to the gravitational load, pressing down on everything below it, while contributing nothing to the energy budget, keeping everything above it from collapsing. The core grows heavier and offers nothing in return. It is mass without purpose, accumulation without support weight, without warmth, and it has been growing for days. The threshold that ends everything is called the Chandrasekhar limit, named for the Indian-American astrophysicist Subrahmanyan Chandrasekhar, who derived it in 1930 at the age of 19 during a steamship voyage from India to England. He was traveling to Cambridge to begin graduate studies, carrying with him a calculation that would eventually earn him a share of the Nobel Prize in Physics more than 50 years later. Chandrasekhar was working on the problem of what supports a white dwarf star against gravitational collapse. White dwarfs are the remnants of low and intermediate mass stars after they shed their outer envelopes. Objects containing roughly the mass of a star compressed into a sphere roughly the size of Earth. The material in a white dwarf is supported against gravitational collapse not by thermal pressure, which requires an ongoing energy source, but by a purely quantum mechanical effect called electron degeneracy pressure. Electron degeneracy pressure arises from the Pauli exclusion principle, one of the foundational rules of quantum mechanics. The exclusion principle states that no two electrons can simultaneously occupy the same quantum state. In normal matter, this restriction is not binding because electrons have plenty of available quantum states to occupy. But in the dense material of a white dwarf where electrons are packed into a much smaller volume, the available quantum states begin to fill up. Electrons are forced into higher and higher energy states, simply to avoid occupying states already claimed by other electrons. This forced occupation of high-energy states creates a pressure that resists further compression regardless of temperature. The crucial insight Chandrasekhar had on that steamship was that this quantum mechanical pressure has a limit. As the mass of a white dwarf increases, its gravity strengthens, compressing the electrons into smaller volumes and forcing them to move faster to maintain their separation in quantum state space. When electrons are forced to move at velocities approaching the speed of light, the relationship between their momentum and their energy changes in a way described by special relativity. The pressure they provide against compression grows more slowly than it would in the non-relativistic case. Above a certain mass, approximately 1.4 solar masses, electron degeneracy pressure can no longer support the white dwarf against its own gravity, even in principle. The quantum mechanical support fails completely. This limit of 1.4 solar masses applies equally to the iron core of a collapsing massive star. When the iron core in the center of Stevenson 2-18 accumulates enough mass to exceed this threshold, the electron degeneracy pressure that had been partially supporting it against gravity fails. There is no gradual weakening, no slow decline, no gentle transition. The support simply ceases to be adequate. The core collapses. What happens in the next second defies any analogy derived from human experience, because nothing in human experience operates at the speeds, densities, or energy scales involved. The iron core at the moment it exceeds the Chandrasekhar limit measures roughly the size of Earth, 10,000 kilometers across. It contains between 1.4 and perhaps 2 solar masses of iron, compressed to densities of perhaps 100 million tons per cubic centimeter, already far denser than any material on Earth's surface, but still orders of magnitude less dense than what it is about to become. When electron degeneracy pressure fails, the core enters freefall. There is no longer any force preventing it from collapsing inward. Material falls toward the center at approximately 1/4. The speed of light, roughly 75000 kilometers per second. In the first tenth of a second, the core compresses by a factor of roughly 1000 in density. In the next tenth of a second, another factor of 1000. The collapse accelerates as density increases, and the distance material must fall decreases. As the density climbs toward the density of atomic nuclei themselves, something changes in the microphysics. Individual atomic nuclei, which had been maintaining their separate identities in the collapsing plasma, begin to merge. Electrons and protons are forced together by the overwhelming pressure, combining through a process called inverse beta decay to produce neutrons and neutrinos. Each such interaction removes an electron from the gas, eroding the electron degeneracy pressure further and accelerating the collapse. The conversion of protons to neutrons proceeds throughout the collapsing core, converting the iron-dominated composition into neutron-dominated matter. The neutrinos produced by this neutronization are unlike any particle stream our experience prepares us for. A neutrino interacts with matter so weakly that a light year of lead would be insufficient to stop most of them. They pass through solid matter as though it does not exist. Under ordinary circumstances, neutrinos produced anywhere inside a star escape immediately, carrying energy away without depositing it. Under the extreme densities of the collapsing core, even neutrinos are temporarily trapped, the density so extreme that even weakly interacting particles cannot escape freely. Within roughly half a second, the infalling material has compressed from Earth-sized dimensions to a sphere perhaps 20 kilometers across. The density at the center has reached and exceeded the density of atomic nuclei, approximately 200 trillion grams per cubic centimeter, a sphere the size of a city containing more mass than our Sun. At this density, the strong nuclear force, which operates only at the incredibly short ranges separating neighboring protons and neutrons in an atomic nucleus, becomes relevant on macroscopic scales for the first time in the universe's history outside of atomic nuclei themselves. And at these ranges, the strong force is repulsive. You cannot compress neutrons together beyond the point where they are touching because the strong force pushes back. The collapse halts, suddenly, violently. The infalling material, still raining inward at a quarter of the speed of light from all directions, strikes the newly formed neutron star core and bounces. The kinetic energy of infall, enormous beyond any human reference point, converts in an instant to the kinetic energy of outward expansion. A shock wave forms at the boundary between the halted inner core and the still infalling outer material and begins propagating outward through the star. This bounce shock carries approximately 10 to the power of 44 joules of energy. Astronomers give this quantity a name, 1 after the physicist Hans Bethe, whose foundational work on stellar nucleosynthesis and nuclear physics underlies our understanding of these explosions. 1 is approximately the energy our Sun will radiate over its entire 10 billion year lifetime. It is released in the bounce in a fraction of a second. The shock wave drives outward through the collapsing material. For a moment it seems like the explosion has already begun, that this wave of energy will simply blast through the remaining stellar envelope and produce the supernova. But the physics is more complicated, and the shock faces an obstacle that threatens to stop it entirely. As the shock wave moves outward through the still infalling iron, it encounters a continuous rain of iron nuclei, moving inward at tremendous velocity. To disassemble these iron nuclei to break the tightly bound iron, 5-6 into its constituent protons and neutrons requires energy. Each iron nucleus the shock encounters and dissociates costs the shock approximately 0.17% of a solar mass equivalent in energy. As the shock processes thousands of Earth masses of iron per second, this energy drain accumulates rapidly. Within roughly 100 milliseconds, the shock stalls. It loses energy faster than it can replenish it, decelerating to a standstill at a radius of perhaps 100 to 200 kilometers from the neutron star surface. The supernova has failed. The shock is dead. The star should, by this analysis, simply collapse entirely into a black hole with no visible explosion at all. And yet we observe supernovae. The mechanism that revives the stalled shock remained one of the great unsolved problems in astrophysics for decades after the basic physics of core collapse was understood. Computer simulations repeatedly produced stalled shocks that died without producing visible explosions. The gap between theoretical prediction and observed reality persisted through the 1980s and 1990s, a gap that became increasingly uncomfortable as detection of neutrinos from supernova 1987A confirmed the basic picture of core collapse, while leaving the explosion mechanism unresolved. The solution involves those neutrinos. The neutron star forming at the center of the collapse is not merely emitting neutrinos as a byproduct. It is producing them in staggering quantities through the continuous neutronization of infalling material and through thermal processes operating at the neutron star surface. In the first 10 seconds after core collapse, the neutron star radiates approximately 3 times 10 to the power of 53 joules of energy in neutrinos. This number is so extreme it requires a moment to absorb. 3 times 10 to the 53rd joules. This is roughly 100 times more energy than the sun will radiate as light over its entire 10 billion year lifetime. It is more energy than the visible explosion will release by a factor of roughly 100. It is the gravitational binding energy of the neutron star being released as the star settles into its final configuration, and almost all of it escapes as neutrinos that will pass through the entire Milky Way through Earth, through your body without interacting with a single atom. Almost all, not quite all, in the region just behind the stalled shock densities remain high enough that a small fraction, perhaps 1% of the outgoing neutrino flux, is absorbed by protons and neutrons. This absorption deposits energy into the material, heating it, driving convective motions, and gradually building up the pressure behind the stalled shock. The process is slow by human standards, taking several hundred milliseconds to accumulate sufficient energy. But the energy available in the neutrino flux is so enormous that even 1% absorption provides enough to revive the shock. Three-dimensional simulations of core collapse developed over the past 2 decades, using supercomputers of increasing power, have revealed that the shock revival is not a simple, spherical process. Turbulent convection behind the shock, asymmetric neutrino heating, and a hydrodynamic instability called the standing accretion shock instability all contribute to a chaotic aspherical explosion. Material flows in along some directions while being ejected outward along others. The neutron star receives a kick in a particular direction as a result of this asymmetric ejection, explaining why pulsars, the rotating neutron stars left behind by supernovae, are observed to move through space at velocities of hundreds of kilometers per second. Once revived, the shock resumes its outward journey through the stellar envelope of Stevenson 2 to 18. For a compact star, a blue supergiant, or a Wolf-Rayet object with a radius of a few solar radii, the shock reaches the stellar surface in hours. The explosion becomes visible quickly after core collapse. For Stevenson 2 to 18, the geometry is entirely different. The shock must traverse not a few solar radii of stellar material, but 2,150 solar radii. At typical shock velocities of several thousand kilometers per second, crossing this distance requires not hours but days. For perhaps a week after the core of Stevenson 2 to 18 collapses and a neutron star or black hole forms at its center, the surface of the star continues burning undisturbed, radiating its dim red light into the surrounding galaxy, completely unaware that the core has already ceased to exist. The information about the core's collapse propagating outward as the shock wave and as neutrinos has not yet reached the photosphere. The neutrinos, traveling at nearly the speed of light, reach the surface almost immediately after escaping the neutron star. They pass through the entire stellar volume as though it contains nothing, depositing negligible energy, and race outward into space at the speed of light. 20,000 years later, they will arrive at Earth, perhaps triggering a handful of detections in the neutrino observatories operating at that time. The shock reaches the photosphere days after core collapse. When it does, the star brightens catastrophically. The shock breakout, the moment when the outgoing shock wave reaches the stellar surface and the explosion first becomes visible to external observers, produces a brilliant flash of radiation across a wide range of wavelengths. For a red supergiant like Stevenson 2 to 18 with its extended diffuse outer atmosphere, the breakout is not a sharp instantaneous flash, but a relatively gradual brightening as the shock propagates through the outermost tenuous layers. The star brightens from its normal luminosity of 400,000 solar luminosities to perhaps several billion solar luminosities over a period of hours to days. At peak, Stevenson 2 to 18 supernova will outshine every other star in the Milky Way combined. The galaxy contains approximately 400 billion stars, contributing a combined total luminosity of roughly 20 billion solar luminosities. For a period of days to weeks, this single exploding star will produce more light than all 400 billion of them together. From a sufficiently distant vantage point outside the galaxy, the Milky Way would briefly appear to nearly double in brightness due to a single stellar death. From Earth 20,000 light-years away, the explosion will be partially muted by the same dust that currently hides the star from optical observation. But supernova explosions are so energetic that they heat surrounding material to temperatures far above the photospheric temperature of the pre-explosion star. The heated dust surrounding Stevenson 2-18 will re-radiate this energy at infrared wavelengths, producing a brilliant infrared transient that infrared survey telescopes will detect, despite the obscuration. At optical wavelengths, the supernova might be detectable to the naked eye if the dust extinction in the optical is not prohibitively severe, potentially appearing as a new star in the constellation Scutum for observers with dark skies and the knowledge of where to look. The spectral classification of the explosion will be Type 2, determined by the presence of hydrogen in the ejected material. Stevenson 2-18's extended hydrogen-rich envelope, the outer layers that give red supergiants their defining characteristic, will be blasted outward by the shock and will dominate the spectrum of the early explosion. The hydrogen-Balmer line's absorption, features produced by hydrogen atoms in specific energy states, will appear prominently in spectra taken during the first weeks after explosion. This spectral signature immediately identifies the progenitor as a red supergiant rather than a stripped star. The total energy released in the explosion, the kinetic energy imparted to the ejected material, plus the radiated energy, will likely approach 1 to the 44 joules. The neutrino energy released simultaneously will be approximately 100 2 orders of magnitude greater. Of all the energy produced in the death of Stevenson 2-18, only about 1% will go into the light and motion of the visible explosion. The other 99% escapes as ghostly particles that pass through the planet you are sitting on without leaving a trace. The neutrino signal from a galactic supernova represents one of the most scientifically valuable events that could occur during the operational lifetime of any neutrino detector. On the 23rd of February 1987, a star in the Large Magellanic Cloud, a satellite galaxy of the Milky Way located approximately 168,000 light-years from Earth, exploded as supernova 1987A. It was the closest supernova observed since Kepler's supernova in 1604 and the first to be detected with modern scientific instruments. 25 neutrinos from the explosion were detected by 3 separate instruments within a span of roughly 12 seconds, 12 by the Kamiokande 2 detector in Japan, 8 by the IMB detector in Ohio, and 5 by the Buxton detector in the Soviet Union. 25 neutrinos from a source 168,000 light-years away, detected among the trillions of neutrinos that passed through each detector without interaction. The handful of detections was sufficient to confirm the theoretical prediction of a neutron star forming in the collapse, to measure the duration of the neutrino burst, and to constrain properties of the neutrinos themselves. The detection earned a share of the 2002 Nobel Prize in Physics for Masatoshi Koshiba. For a galactic supernova, like the eventual death of Stevenson 2-18, the neutrino flux at Earth will be vastly greater. The distance is 20,000 light-years rather than 168,000, roughly 8 times closer, meaning the flux is roughly 64 times higher for the same source energy. Modern neutrino detectors are also far more sensitive than those operating in 1987. The Super Kamiokande detector in Japan contains 50,000 tons of ultra-pure water, compared to the 2140 tons in Kamiokande 2. The Ice Cube detector at the South Pole instruments a cubic kilometer of Antarctic ice with over 5,000 light sensors. Estimates suggest that a galactic supernova at a distance comparable to Stevenson 2-18 would produce thousands to tens of thousands of neutrino detections in Super Kamiokande alone, over a burst lasting approximately 10 seconds. The resulting dataset would provide an unprecedented window into core collapse physics, constraining the neutron star equation of state, the explosion mechanism, and fundamental properties of neutrinos with precision impossible from any other source. The neutrino burst will arrive at Earth several hours before any electromagnetic brightening because the neutrinos escape the core immediately, while the shock wave requires days to reach the stellar photosphere and produce observable light. This advance warning is precisely the purpose of the supernova early warning system. an international network of neutrino detectors linked to provide rapid alerts to electromagnetic observatories when a galactic supernova neutrino burst is detected. A snooze alert triggered by Stevenson 2-18's collapse would give astronomers hours to point every available telescope toward the constellation Scutum before the explosion becomes visible, capturing the crucial early phases of shock breakout that have never been directly observed. The material ejected by the explosion will expand outward at velocities reaching 10,000 kilometers per second in the fastest-moving layers, decelerating over centuries as it sweeps up surrounding interstellar material. For Stevenson 2-18, the ejected mass will likely include 10 to 20 solar masses of processed stellar material, the hydrogen and helium envelope, the products of shell burning from various evolutionary phases, and the heavy elements synthesized in the extreme conditions behind the shock during the explosion itself. This last category, the explosive nucleosynthesis products, includes elements that cannot be produced through any other mechanism in sufficient quantities to explain their cosmic abundances. The rapid neutron capture process, called the R process, requires the extreme neutron densities and temperatures prevailing in the shock-heated ejector to build nuclei far heavier than iron by successive neutron captures, followed by beta decays. Gold, platinum, mercury, lead, uranium, thorium, and dozens of other heavy elements are produced in these conditions and scattered into the interstellar medium with the expanding ejector. Every atom of gold in every piece of jewelry ever crafted passed through conditions like those in a collapsing stellar core before arriving in the solar nebula that formed our sun. Every atom of uranium in every nuclear reactor ever built was synthesized in the death throes of a massive star. The lead in ancient Roman water pipes the mercury in 19th century thermometers, the platinum in catalytic converters. All of it traces its origin to stellar explosions occurring in the billions of years before our solar system formed. The death of Stevenson 2-18 will add to this cosmic inventory. The heavy elements produced in its explosion will mix with the interstellar medium over millions of years, diluting into the surrounding gas and dust, eventually becoming incorporated into new molecular clouds that will collapse into new stars and, around some of them, new planets. The atoms scattered by Stevenson 2-18 supernova may one day form the bones of creatures living on a world orbiting a star, not yet born from a cloud, not yet assembled from gas, not yet enriched by this star's death. At the center of the expanding debris, the collapsed core will remain as one of two possible objects, and which one forms depends on physics that our current theoretical understanding cannot predict with certainty for a progenitor like Stevenson 2-18. If the mass remaining in the collapsed core after the explosion falls below roughly 2 to 3 solar masses, a neutron star will form. Neutron stars are among the most extreme objects that can exist in stable form, packing more mass than our sun into a sphere 20 kilometers across, creating surface gravities approximately 200 billion times stronger than Earth's. The density of a neutron star exceeds the density of atomic nuclei, a teaspoon of neutron star material weighing roughly 400 million tons. A neutron star born from Stevenson 2-18 will be spinning rapidly due to a consequence of physics familiar from spinning figure skaters. As the original stellar core, rotating perhaps once every few months, collapses by a factor of roughly 50,000 in radius, conservation of angular momentum requires the rotation rate to increase by the square of that factor. A slow rotation once every few months transforms into a rotation perhaps hundreds of times per second. Combined with the intense magnetic fields generated during the collapse by compression of the original stellar magnetic field, the young neutron star becomes a pulsar, a rapidly rotating lighthouse that sweeps beams of radio waves across the sky with metronomic precision. If, however, the mass remaining in the collapsed core exceeds this threshold, neutron degeneracy pressure cannot support it against gravity. No known force in the universe can halt the collapse. The core continues compressing beyond neutron star densities past any state of matter we can describe into a black hole, a region of space-time where the curvature becomes so extreme that the escape velocity exceeds the speed of light. For Stevenson 2-18, the outcome is genuinely uncertain. The initial stellar mass was perhaps 25 to 40 solar masses. The current mass after millions of years of red supergiant mass loss is perhaps 15 to 25 solar masses. Of this, perhaps a few solar masses will remain in the collapsed core after the explosion blasts away the outer layers. Whether this remnant mass falls above or below the neutron star black hole boundary depends on explosion dynamics that three-dimensional simulations are only beginning to resolve. The uncertainty is real. The physics does not yield a clean answer for a progenitor of this mass range. Stevenson 2-18 sits in what theorists call the mass gap region, where the outcome of core collapse is sensitive to details of the explosion mechanism, the neutron star equation of state, and the distribution of angular momentum in the pre-collapse core. Different simulations using slightly different input physics produce different outcomes for stars in this mass range. We do not know whether a neutron star or a black hole waits at the center of Stevenson 2-18's eventual debris cloud. We may not know until the explosion occurs and the nature of the remnant reveals itself through its behavior in the years and decades following the supernova. What we do know is that the information about whether this has already happened is traveling toward us right now or has not yet begun its journey, and we cannot know which. The core of Stevenson 2-18 might have collapsed thousands of years ago. The neutrinos from that collapse reached Earth thousands of years ago, passing through every human being alive at the time without a single interaction undetected because no instrument capable of detecting them existed. The shock wave from that collapse has been expanding through the stellar envelope for thousands of years, or has already broken through the photosphere and begun its journey toward us as electromagnetic radiation. Those photons might currently be racing across the 20,000 light-year gap, carrying news of an event that ended the largest known star before the first pyramid was built. Or the collapse lies in the future, perhaps hundreds of thousands of years in the future, with silicon still burning in the core, or the silicon burning not yet begun. The surface we observe tonight reflects conditions from 20,000 years ago. The star, as it exists at this actual moment on this actual night, is forever hidden from us behind the finite speed at which information can travel. This temporal uncertainty, the permanent inability to know the current state of any distant object, is not a limitation of our instruments or our ingenuity. It is written into the structure of the universe itself by the absolute speed limit that governs the propagation of information. We live in a cosmos where looking outward means looking backward in time, where the most distant objects we observe are the youngest version of what they are, where we can never know the present state of anything beyond the narrow light cone of our immediate neighborhood. The largest known star burns tonight, or it burned 20,000 years ago, and no longer exists. We have found it. We have measured it. We have understood its structure, its history, and its fate, as well as physics and technology permit. But whether it is alive at this moment, we cannot know. That uncertainty is not a failure of science. It is the shape of the universe we inhabit. You began this journey with a star you could not see, a name in a catalogue, a data point in a systematic survey conducted by an astronomer who had no idea what he had found, a bright infrared source buried behind 20,000 light-years of cosmic dust, invisible to every telescope that had ever been pointed at the sky, before the infrared era made seeing through that dust possible. You began with a star that had been burning in complete obscurity for the entire history of human observation, undetected through all of recorded civilization, through every war and dynasty and empire, through every generation of astronomers who mapped the constellations and measured the heavens without knowing this particular monster existed. Now you know what was hiding there. A star 215, 0 times the diameter of our sun, containing a volume 10 billion times larger, radiating energy equivalent to 440,000 suns, combined with an average density lower than the air in the room where you are sitting. A star whose surface is cool enough for molecules to form, where titanium oxide and water vapor drift through an outer atmosphere that qualifies as a near-perfect vacuum by any terrestrial definition. A star whose individual convection cells span distances larger than the orbit of Jupiter, whose pulsation cycle lasts years, whose surface gravity is so weak that material barely needs a push to escape into surrounding space entirely. A star that has been steadily shedding solar masses of material into the galaxy over tens of thousands of years, building up a circumstellar cocoon of enriched gas and dust that glows in the infrared like a memory of its own self. If you placed it at the center of our solar system, it would swallow Mercury, Venus, Earth, Mars, and Jupiter. Saturn would graze its surface. That is what exists 20,000 light-years from where you are sitting right now. But the true weight of what you have learned is not contained in those numbers, as staggering as they are. Numbers at this scale pass through the mind without leaving permanent marks. They are too far from anything experiential to anchor themselves to genuine understanding. What carries weight is something else entirely. It is the fact that this star existed completely unknown throughout the entire human story. Every person who has ever lived, every civilization that rose and fell, every generation that looked up at the night sky and tried to make sense of what they saw, lived and died without knowing Stevenson 2-18 was there. The ancient Greek astronomers who built the first quantitative framework for understanding the heavens never knew. The Islamic scholars who preserved and extended that framework through the medieval period never knew. Galileo turning his telescope toward Jupiter and discovering its moons never knew. Herschel mapping the structure of the Milky Way never knew. Hubble establishing that the universe contains billions of galaxies beyond our own never knew. All of them built their understanding of the cosmos on a foundation that was missing this particular fact, this particular data point about what the universe is capable of producing. We are the first generation of humans who know. Consider what that knowledge required. It required semiconductor physics developed in the 20th century to build infrared detectors sensitive enough to see through cosmic dust. It required optical engineering refined over decades to build the interferometric instruments that can measure angular diameters smaller than the apparent width of a human hair, viewed from 10,000 miles away. It required a satellite launched in 2013 to measure the positions of 2 billion stars, with precisions approaching 10 micro-arcseconds, accumulating data over years of operation before releasing the parallax measurements that provided the distances required to convert angular sizes to physical dimensions. It required theoretical astrophysicists working across a century to develop the atmospheric models connecting observable brightness and temperature to physical radius through established physical relationships. Every piece of this was necessary. Remove any one element and Stevenson 2-18 remains unknown, a bright infrared source in a catalog, a data point without interpretation. The discovery of the largest known star is, in this sense, not the achievement of any individual or any single moment. It is the cumulative product of human scientific civilization spanning centuries of patient accumulation, each generation adding its contribution to a structure of knowledge that no single lifetime could build. There is something that must be said about the light itself. The photons that informed the measurements confirming Stevenson 2-18 as the largest known star are ancient in a way that most scientific data is not. Infrared photons detected by ground-based observatories and space telescopes, photons carrying information about the temperature and luminosity of a stellar surface, left that surface 20,000 years ago. 20,000 years ago, the last ice age had not yet ended. The Great Ice Sheet still covered much of North America and Northern Europe. Human populations were small and scattered, living in family groups, hunting megafauna across landscapes that have since transformed entirely. Agriculture had not been invented. Writing had not been invented. The wheel had not been invented. The city had not been invented. Every subsequent development in the human story, every civilization, every empire, every war, every discovery, every piece of art and music and literature, every scientific advance, including the infrared astronomy that eventually detected this star's light, all of it unfolded in the time those photons spent crossing the space between Stevenson 2-18 and the telescopes that caught them. The star we know is not the star as it is. It is the star as it was when our ancestors were crossing land bridges and painting cave walls and learning to survive in a glacial world. The present-day Stevenson 2-18, the star, as it exists at this moment, is hidden from us behind 20,000 years of light travel time as inaccessible as the future. We have measured a ghost, an echo, an ancient signal from an object that may no longer exist in the form we have measured or may persist unchanged for hundreds of thousands of years to come. The uncertainty is absolute and permanent, and built into the fabric of the universe by the same physical laws that make the star's existence possible. The philosophical weight of this uncertainty is not merely abstract. It applies to everything you observe when you look at the night sky. The moon you see is the moon as it was slightly more than a second ago. The sun is the sun as it was 8 minutes and 20 seconds ago. The nearest star, Proxima Centauri, is as it was 4 years and 3 months ago. The Andromeda Galaxy, the most distant object visible to the naked eye, is as it was 2.5 million years ago, before our genus had yet evolved. Every photon that reaches your eye carries news of a past, separated from the present by the time that light required to cross the intervening distance. The universe you see is not the universe as it is. It is the universe, as it was at a different time for every object. You observe a composite of moments separated by anything from seconds to billions of years, assembled into a single visual field that your mind interprets, simultaneous. The night sky is a temporal mosaic, a collage of different pasts, displayed as though they share a single present. Stevenson 2-18 sits at one extreme of this mosaic for objects within the Milky Way. Its contribution to the galactic infrared sky represents a past more remote than any development of human civilization. And yet it is one of the closest galactic objects, compared to the stars at the far edge of the Milky Way, 100,000 light-years from Earth, whose light represents a past measured in geologic time. And what does it mean that matter has organized itself in this way? That the same physical laws governing the behavior of subatomic particles also permit under the right conditions the assembly of objects 2150 times the diameter of our Sun. That the same quantum mechanical rules that determine the electronic structure of atoms also set the Chandrasekhar limit that will eventually end Stevenson 2-18. That the same gravity pulling the apple from the tree also accumulates gas clouds into stars and maintains the precarious equilibrium that allows those stars to shine for millions of years before collapsing. There is a continuity running from the smallest scales of physics to the largest scales of astronomy that deserves more than passing acknowledgement. The universe is not a collection of separate phenomena operating according to separate rules at different scales. It is a single, deeply interconnected system with the same fundamental laws, producing wildly different outcomes depending only on the quantity of matter involved and the time allowed for those laws to operate. Hydrogen, the simplest element, the most abundant substance in the universe, collapsed by gravity into a ball of sufficient mass, sustained by nuclear reactions for millions of years, expanded by shell burning into an envelope of near vacuum spanning billions of miles, is Stevenson 2-18. Nothing more exotic than that. The same element that makes up most of the sun, most of the gas between the stars, most of the observable matter in the universe, organized by the same gravity that holds you to the ground, becomes the largest known star when circumstances allow. The universe does not require special materials or special conditions to produce its most extreme objects. It requires only sufficient mass, sufficient time, and the uninterrupted operation of physical laws that apply equally everywhere. You are made of the products of stars like Stevenson 2-18 that lived and died before the solar system formed. The oxygen in your lungs was synthesized in the helium and carbon-burning shells of massive stars. The calcium in your bones came from silicon burning. The iron in your blood, the element that will eventually doom Stevenson 2-18, is the same element that forms in the cores of massive stars and seizes their nuclear furnaces into silence. The phosphorus in your DNA, to the copper in your neurons, the zinc in your enzymes, all trace their origins to stellar explosions that scattered enriched material across the galaxy billions of years before Earth existed. You are the downstream consequence of stellar death. You are what the universe does with the material it has already processed through stellar interiors and scattered back into the interstellar medium through supernova explosions. The atoms in your body have each traveled an extraordinarily long road from the first generation of stars formed after the Big Bang through successive rounds of stellar birth nuclear processing and explosive dispersal, eventually assembling in a molecular cloud in an outer spiral arm of an ordinary galaxy, collapsing into a star and a planetary system, and finding their way into the chemistry of a living organism that can ask questions about where it came from. The largest known star and the creature contemplating it share the same physical origin. Both are products of the same hydrogen produced in the first minutes after the Big Bang, processed through the same nuclear reactions in the same kinds of stellar interiors, governed by the same physical laws, participating in the same ongoing cosmic story that has been unfolding for 13.8 billion years and will continue long after Stevenson 2-18's remnant has cooled into darkness. The record Stevenson 2-18 holds will not stand forever. Some future survey using instruments not yet built will characterize stellar populations in regions of the galaxy not yet accessible to current technology. Among the several million red supergiants estimated to populate the Milky Way, most unmeasured, some may exceed 2150 solar radii. The physics permits it. The theoretical maximum lies somewhat above the current measured record. Whether anything larger actually exists waits only on the expansion of the observed sample, or the record will stand. Improved surveys will find nothing larger. The distribution of red supergiant sizes will converge under the scrutiny of new instruments on a true upper boundary near Stevenson 2-18's dimensions, validating the theoretical prediction that we have found the limit of what stellar physics allows. Either outcome is scientifically meaningful. Either the universe is more extreme than we have yet found, or we have reached its edge and can say with confidence, this is as large as stars get. Neither conclusion diminishes the star itself. Stevenson 2-18 exists. That is the fundamental fact. Not as a theoretical prediction, not as a computer model, not as a speculation about what the universe might contain in its unexplored regions, but as a confirmed, measured, physically real object burning in the constellation. Scutum 20,000 light-years from where you are sitting. We found it. We measured it. We understood it within the framework of physics that humanity has assembled over 4 centuries of systematic inquiry into the nature of reality. That this understanding is possible at all is extraordinary. We are creatures of roughly 2 meters height, living on a rocky planet, orbiting an ordinary star with lifespans measured in decades. We have never left our own solar system. We have never touched another star. We will never visit Stevenson 2-18, never stand in its near-vacuum outer atmosphere and look outward at the surrounding galaxy from within a stellar volume large enough to contain the inner solar system. And yet we know it. We know its diameter, and its temperature, and its luminosity, and its mass, and its distance, and its evolutionary history, and its eventual fate. We know what it is made of, and how it formed, and how it will die, and what it will leave behind. We know these things not through any direct experience of the object, but through the patient accumulated work of human minds, applying mathematical reasoning to ancient photons, building an understanding of the cosmos that exceeds in scope anything our physical limitations would seem to allow. This is what science is, not a collection of facts, but a method of extending human awareness beyond the boundaries of human experience. An instrument for knowing things that cannot be directly touched, visited, or observed, except through the faint signals they send across space and time to whoever has built the instruments to receive them. The infrared photons that confirmed Stevenson 2-18 as the largest known star have completed their journey. They left a surface 20,000 years ago, crossed the galaxy through clouds of dust that absorbed and scattered almost every companion photon they began the journey with, arrived at the mirrors of telescopes built by a civilization that did not exist when those photons were emitted, and yielded their information to instruments that converted them to digital signals and data points in computers. From those data points, the size of the largest known star, there is something in this that resists being fully articulated but insists on being acknowledged. A photon born in the outer atmosphere of a star, 2150, times the diameter of our sun traveling for 20,000 years through the dark, between the stars arriving at precisely the moment when human civilization had developed both the instrument to receive it and the theoretical framework to interpret it, and revealing in that arrival the most extreme stellar object yet found in the observable universe. The timing required no design. It required only patience. The photons were always on their way. The instruments eventually arrived. Tonight, more photons from Stevenson 2 to 18 are completing that same journey. They are arriving at the mirrors of infrared observatories and being converted to data. They are telling us about a stellar surface that existed when the ice sheet still covered the northern hemisphere, carrying news from a star that may still be burning or may have already died in a supernova, so brilliant it briefly outshone the entire galaxy, an event whose light, if it has occurred, is still somewhere in the 20,000 light-year gap between that explosion and our telescopes. We are waiting as we always have been for the light to arrive. We are small, we are brief. We live on a speck of rock orbiting an ordinary star in an unremarkable corner of a galaxy that contains 400 billion other stars, many of them stranger and more extreme than our Sun, and one of them the largest known object of its kind in the observable universe. Against this backdrop, the entire human story, every birth and death and discovery and catastrophe fits within a volume of space so small that from Stevenson 2 to 18, our Sun would be invisible to any instrument we have ever built. And yet, we found the star, we measured it, we understood what it is, how it formed, what burns inside it, and what will eventually end it. We extended human knowledge to encompass an object 20,000 light-years away, invisible to our eyes, hidden behind dust that blocks 100 million times the light we could otherwise receive, and we determined its dimensions to within a few hundred solar radii. The universe has produced in us something that can comprehend its own extremes. That comprehension does not make us large. It does not place us at the center of anything. It does not grant us permanence or significance in the cosmic accounting. The Sun will exhaust its hydrogen in 5 billion years. Earth will be uninhabitable long before that. Every trace of human civilization will eventually dissolve into the expanding entropy of a cooling universe. The stars themselves will burn out, the last red dwarf fading to darkness in roughly 100 trillion years, and after that nothing but black holes and cold remnants in an expanding void. Against that backdrop, we are brief beyond any word that captures brevity. But in this moment, on this world orbiting this star, we know the largest star in the observable universe. We have measured its diameter and understood its physics and traced its history and predicted its death. We have done this by building instruments that see in wavelengths our eyes cannot register by applying mathematics. Our ancestors could not have conceived by standing on the accumulated knowledge of every generation that studied the sky before us. The photons from Stevenson 2 to 18 have been traveling for 20,000 years. They do not know they carry information. They do not know they will be received. They do not know that on a small planet, in an outer spiral arm of the galaxy, creatures have built mirrors and detectors and computers and theoretical frameworks capable of reading from their ancient arrivals the dimensions of the star that sent them. The photons arrive. The instruments receive them. The knowledge accumulates. And somewhere in the constellation Scutum 20,000 light-years from here, the largest known star either still burns or has already died, in a flash that will reach us one ordinary night, unannounced, as a brief brightening in the infrared sky. We will be watching. We have always been watching. That is what it means to be the kind of creature we are.